Welcome to Receding Horizons, a podcast for exploring topics in astronomy and space science. Since antiquity, humans have gazed at the night sky, attempting to decipher its mysteries and find our place within it. As astronomer Edwin Hubble once remarked, the history of astronomy is a history of receding horizons. Our podcast will attempt to answer some of the biggest questions from the oldest of sciences. The mission of this podcast is to explore topics of astronomy and space exploration and share them with the community of Brownsville, Texas. Our valley is entering into the next phase of human space exploration and participating in the era of multi-messenger astronomy. We are providing a forum of discussion among people of all ages and expertise to bring awareness about our role in this next exciting era. These are Receding Horizons.
Did you make coffee? Do you have coffee?
And not funny story, actually.
Drinking water.
That's
Me
good.
too.
I have water too.
On top of the coffee.
I just
On top of the coffee. Yeah.
both at the same time. Yeah, there's water in the coffee.
Yes.
So earlier this week, I was in a meeting with one of my for my job with the Argentinian people, and they had you've seen Mario with the mate thing.
Yeah.
And one of them had that, and I've been drinking way too much coffee lately, and so I remembered about that, so I ordered some stuff on Amazon, and it came in today. So I tried it out, and I think I failed horribly because it was bad, not like I remembered it. So I need to get better at that. But I've heard that that's just a really good replacement for like energy, and that it cleans you out pretty well. I'm not quitting coffee. I just I don't think 5 or 6 cups a day is doing me good.
No, I don't think so.
No. Probably not.
Moises, do you still drink mate?
Every once in a while, occasionally. It is a good pick me up. I will give you that.
Yeah.
Yeah, even the little bit that I drank, I know I prepared it wrong, but it still felt pretty good.
Was it bitter?
Yeah, I was getting, Moises, maybe you can tell me, I was getting like some of the actual particles in my mouth. I feel like that shouldn't happen.
Yeah, maybe. So you said you tried to prepare it yourself? Like you have the cup, you have the straw, the bombilla?
Yes,
Yeah.
I have everything, yes.
Okay, so like it itself, right, is a process, and so there is it's a process that's embedded with tradition, right? And so Richard knows exactly what I'm talking about.
There is a learning curve for your first time.
Yeah, and also the first one that I made was extremely bitter. And so it is a bit of a learning process, kind of trial and error, but also it's one of the things that is embedded with this tradition and in its culture of the drink itself is that you get to prepare it how you like it, and so that's pretty much it. One of the things that controls the bitterness really is when you do the prep, that this is like really, really, really fine dust, and the goal is to try to remove as much as the fine dust as you can. Well, that essentially controls the bitterness.
Okay, yeah, that's what it was. There was a lot of dust in there.
Yeah,
Like dust in the loose stuff that you're brewing. So you want to like sift that? Is that what you're saying? Like get rid of that, or?
yeah, but it's not so much, and by dust I don't mean like there's like dirt in there, right? Like fine part. That's not what I mean. It's it's just, since we like this product comes from Argentina, right? The like true mate comes from Argentina, from the yerba mate, and so it's a pile of sticks. And during the shipping process, there's a lot of friction, and so you get this really fine dust of mate, like particles. And if you don't take that out, like if you don't do anything to it and you just include a lot of that powder, it'll be very bitter. Yeah.
Interesting. So it's like pretty much like dead cellulose or whatever plant material that adds the bitterness to the tea. Interesting.
Yeah, in the video I saw, one of the first step is you have to cup it and then go like that, And then when you look at your hand, it's just, yeah, it's all that dead.
So what's the process like in general? I don't know who wants to explain that.
Moises, say it, and I'll try to
We're
find
recording, by the
where
way,
I went
so.
wrong. Oh,
Okay.
yeah.
Yeah, this is just, we're just going with it.
Yeah. So so they say like you grab the cup and you fill it about 3/4 of the way, and then you cover the top, and then you flip it, and if you look at your hand, like you'll have that fine dust on your hand, so then you clear it off. I what I do is my mate cup is one of the modern type, right? So it's like it's metal. It's not one of the traditional wooden types. And they use so many different materials for this, but the cup itself, if what I do for mine is I actually go around the cup and like take it off with my finger, dust my finger off, and then I go again, dust it off, go around the rim, because it collects. Though at least the mate that I have in my stock, it has a lot of dust. So I do that, several times until either one, I just want to drink mate, or two, I'm not collecting so much on my hand anymore. There still be some on along the rim, but like you notice every iteration is a lot less, and then let's say you grab the cup, you kind of sift it so it's flat, and then you angled it a little bit, and so then and you give it a little shake, and so if you can imagine, like the leaves are like this, right? And so when you give it a little shake, it levels out, so you end up with a little wedge when you put it back. Then you want to wet the tea, the tea leaves. And so also, right, mate is loose, just it was like loose leaf, right? It's just like loose sticks and loose sticks and leaves. And so then you wet it, and it kind of maintains its shape. It kind of maintains its shape. And then and so you wet all of it cautiously the first time, but you want to preserve this wedge shape, and then you start pouring in some of the water towards the lower side. Once you have a little bit of water going on in there, what you need to do is you grab your bombilla, and which was the straw, right?
Mm-hmm.
And you top it, so you don't want anything going into the straw. So you have it closed, and you push it in to this angled spot, and then you push it out, so that way the bombilla sits right on the deepest end of the tea. And then you keep on pouring. The way that I was taught to do it, you should put the hot water directly over the straw, right, or over the bombilla. That way it kind of what's the word, like decanter, right? So like you're pouring the water so it hits the straw, and it doesn't like mess with the leaves too much, because you want to preserve this shape as much as possible. And you fill it up, and kind of slow, right? If you think about it, you're what's the word, steeping, right? So you're steeping the tea, but you're controlling how long you're doing that, and how much water is actually going into it. So you wet them, but you don't want the water to like completely screw up the thing that you have going on up here. So you let it come up, and but not all the way, right? You let it come up a little bit, you see that it sucks it in, you put some more water, you see that it comes back in, and but you don't go too high up on that angle that you have, right? Just enough. And what I like to do is I wait until it's no longer soaking into the bottom. So then, like, I can see a little bit of the water there, and it is the person who prepares the tea is called the cebador, and so it's the responsibility of the cebador to drink the bitterness, because the first one is is the most bitter.
Oh.
Yeah. The first sip is the most bitter, and it's the most concentrated, right? And so that's why the person who prepares it has to drink the first one. Then after that, it's up to them if they want to share, which is the traditional custom. So then you follow the same rules. When you fill it up again, you fill it up to essentially where the wet line is. So there's still dry leaves up in the top, and you want to preserve those dry leaves as long as possible. But through the natural process, right, the water line will be or at least like those dry tea leaves will start getting saturated with water with every cycle that you go through it. Yep. And so
how did you learn all of this? Like, was this taught to you by one person, or was this just accumulated over time, looking stuff up, etc.?
Is a combination of both, right? So Carla, right? That she came from Argentina and taught us so many things. Yeah, Carla. She taught us so many things about just astronomy, right? Doing observational astronomy and essentially how to rough it as a as an astronomer. But in that was also preparing the mate, and yeah, so that was a cultural awakening, right? And with in terms of mate specifically, but also a lot of YouTube. Yeah,
A lot of YouTube.
Yeah.
Cool. So I know where I went wrong immediately. I didn't, with the first time you pour the water, I don't think I poured it on all of the mate that was there. So it did not hold its integrity. So when I poured the hot water, it immediately just went all over the place. I'll learn. But everything you said about it being a learning process gives me a little bit of hope.
Yeah. Yeah, that's pretty much it. It's a big big learning process.
Just like roughing it as an astronomer, as you said, which is, I like that phrase. That's how well, at least I think Moises and I became astronomers, was roughing it and repeatedly learning things and failing and getting better each time.
Yeah.
Wow, we've never had the episode name so early in the podcast.
Mate.
I was thinking roughing it as an astronomer.
Astronomer explains how to make mate. Yeah. Yeah. So, I guess we did it slightly out of order, but I actually like this way better. I have an introduction. Should I read it at this point, or?
Yeah, go ahead.
Okay, so I'll start with the excerpt. Nothing puts human existence into context quite like contemplating the cosmos. What you might not guess, sitting comfortably in your living room with a glass of wine and a good book, is that what's happening in your immediate neighborhood is dramatically affected by the evolution of the whole universe. Many of the most important features of our lives here on Earth, our notion of the passage of time, the existence of causes and effects, our memories of the past, and freedom to make choices about the future, are ultimately consequences of conditions near the Big Bang. To get a hold of the big picture, we need to put ourselves in cosmological context. It's hard not to be moved when looking at the night sky. In true darkness, far away from the all-pervasive lights of human civilization, the inky black background comes alive with thousands of stars, a handful of planets, and the majestic sweep of the Milky Way galaxy stretching from one horizon to the other. It's also hard to grasp the true extent of the universe on the basis of what we see when we look at the sky. There is no sense of scale, no familiar landmarks by which to judge size and separation. The stars bear a close resemblance to the planets, even though we now know they are quite different. They look nothing like the sun, although now we know they are very similar. It's not surprising that ancient cosmologists, when theorizing about the universe, took as its fulcrum the thing they understood the best, themselves. Cultures scattered throughout history have devised a number of imaginative cosmological scenarios, and they tended to share a common conviction that our home, the Earth, was somehow special. Sometimes Earth was at the center of it all. Sometimes it was at the bottom. Very often, it held particular significance for whatever force or God was responsible for creation. One way or another, there was a shared belief that we mattered in the great scheme of things. It wasn't until Giordano Bruno, a 16th century Italian philosopher and mystic, that anyone suggested that the sun was just one star among many, and the Earth one of many planets that orbited stars. Bruno was burned at the stake for heresy in Rome in 1600, his tongue pierced by an iron spike and his jaw wired shut. His cosmological speculations were probably not the part of his heresy that the church found most objectionable, but they didn't help any. Today, We understand a great deal about the scale of the universe. Bruno was on the right track. Cosmically speaking, there's no indication that we matter at all. That's chapter 6, at least the beginning of chapter 6, Our Universe, from Sean Carroll's The Big Picture on the Origin of Life, Meaning, and the Universe Itself. And also, I'm reading the copy that Victor let me read. So,
Best book. Shout out Sean Carroll.
Sean Carroll, you can come on the podcast anytime.
Invite me.
So this is the episode on astronomy.
Because we have the astronomer, the one who taught us all.
Yeah, so I think it's worth mentioning that we originally recorded a version of this, last summer, so many months ago. We were with Moises at Richard's apartment here in Brownsville, and it was a great conversation. And so, yeah, I'm excited for this one, and let's try to make it half as good as that one.
You know, we could begin that. I'm glad you brought that up because I was listening to that podcast, that audio recording just before us talking today. I think we could start I can start with, I even wrote an introduction for Moises. I was going to run it by him first, but I guess I have to go on my own here. So I apologize if I get anything wrong and you should correct me. So.
All right. We'll see. And
yeah, exactly. So our guest this episode is our collaborator, colleague, and friend, Moises Castillo. A Brownsville and Los Fresnos native, Moises attended university and earned a Bachelor of Science in Physics from the University of Texas Rio Grande Valley, during which he also worked as lab manager in the physics department. Moises earned a Master's of Science in Physics from UTRGV in 2019. He's been the assistant director of the Cristina Torres Memorial Observatory, where he observed and studied eclipsing binary star systems, as well as a researcher for the Center for Gravitational Wave Astronomy at UTRGV, working under Mario Diaz. Currently, he's stepping into his role as the event coordinator for the space science team of the South Texas Astronomical Society. He's a curious explorer of the world, a talented engineer, an astronomer, the authoritative MC voice, and a great travel partner and friend. Moises, welcome to Receding Horizons.
Thank you. So I think that introduction was great.
Didn't get anything wrong?
No, I don't think so.
Good, because I listened to what your introduction was on the last one, and I just listened to what you said, and I thought the way because I remember the best part about that episode that we did was telling your story. That was like the majority of that, at least that first half, and I loved how you told your story. How you included your parents and your family and all of that. So, yeah.
No pressure this time.
No pressure this time. It's going to be like, so the story is, and then it's going to cut to whatever it was. The version from last time.
No one will know. No one will know.
Yeah. So I guess what I could say is what I could ask is what I asked last time. So who are you? Because that's literally how I asked it last time. But I wrote, "Who is Moises Castillo?"
What are you doing in my apartment?
What are you doing? You remember? Oh my God!
Is that I was just saying that as
that's what I said. Yeah. Wow. I thought you. Wow. Okay. So what are you doing in the Zoom room? I guess is a better question to ask.
All right. What am I doing here? So I was invited. Also, it seems my internet is currently unstable. So this is
Yeah, sorry, that was a bad setup. That was a tough setup. Like, why are you here? It's like, go.
One of the added challenges of today's world, right?
Better question would be, well, how did Moises Castillo end up doing what he's doing now? Why are you talking to Victor and I? And where did it all begin? How did it all begin for you?
Yeah. Okay. So present time. where did it all begin for me? So there is well, I don't know, let's see. So this means an interest in astronomy. You know, it's like this innate curiosity that I carry just of the world that's around me, right? I I'm not exactly too sure how it came about, how it was, you know, successfully nurtured after, you know, so many years of being curious. I'm still curious about just uh, how everything works, and how everything is like happening, you know. And so, you know, as a child in Los Fresnos, it was far away enough from big city lights that um, still being in the city limits, you can see tons of stars, you know. And this was something that I used to do with my friends. We would just stargaze. So literally just like lay outside, look up, see if we see things moving, hope they're aliens, you know. And yeah, and this was pretty much it, you know. Like we would spend a lot of time just, you know, talking about, you know, possibilities, um or impossibilities, right? Just of the world and the things that we would see then. um I would watch a lot of TV, a lot of documentaries growing up. And I would always see there was that title that would pop up next to the person who was speaking in the documentaries that I enjoyed the most. And most of the time the title would be physicist. You know, it's kind of a shame I don't remember who they were. So I never, like, if you were to ask me like who is my idol, you know, or like who did like, I don't have one in particular from those times. It's just something like a trend that I would see, right? So it's like physicist, astrophysicist. um and I guess more up until more recent times, right, that I could start naming people that I see on TV. But like that's not how it was growing up. It wasn't the people that interested me. It was what they were doing, you know. And the that was it, right? So like I was hooked on TV. This was, you know, elementary school, middle school. So I grew up with a lot of TV. but but aside from that, you know, probably, you know, I should also give a shout out to my teachers growing up too. That's something that when I've talked about it in the past, I don't think I've mentioned them before. But like I remember growing up, I always enjoyed my science teachers, um, and you know, also my math teachers. Um, they really like today. When I think about people taking classes, they're like, why do I even need any of this stuff? I'm never going to use it. Like, okay, maybe you, but like this is stuff that like I might need to use tomorrow or even today, later today, right? So it's almost an everyday thing of the stuff that they taught me back like as early as middle school, for sure, right? I mean, technically, there's like the basic arithmetic that we learned like back in elementary, um but yeah, right. So like growing up, and so from middle school into high school, I still maintained that same curiosity, right? Though my friends and I wouldn't necessarily, you know, be stargazing as frequently as we used to from elementary to middle school. We would still try, you know, to hang out, then look up at the stars. But you know, we start developing our persons more during those times, and so interests broaden probably as well. And but in high school, I was given a pretty cool opportunity. I remember it was in the chemistry class. Um, it was the assistant principal from my middle school that came in, and he's like, "Hey, y'all, like I'm here." Oh, no, it was an email. The first time was an email, and the our chemistry teacher got an email, and she's like, "Hey, y'all, who'd want to go to college?" And then like, boom, immediately I raised my hand, and it's like, "Oh, you know what? I'm sorry, that email didn't apply to y'all." I'm like, shucks. Okay. This was sophomore year of high school. This is sophomore year of high school, and so that's year 2 of 4 in the traditional sense for high school. Then it happened the second time, except that this time somebody came into the classroom to talk to us, and that was it, the assistant principal from, or the previous assistant principal of the middle school there, and he's like, all right, so who wants to go to college? You know, I raised up my hand, and he's like, there's a really great opportunity, and it was at the time a pilot program for a very well-established program now, the Math and Science Academy at now UTRGV. It had started at then, you know, the legacy institution, UT Brownsville, and it was a really small class for us to start with. I think the starting class was about 30. The graduating class was close to 30, and so I am one of those. The love of my life was also one of those. Yeah, so that's actually where we met, and so we were high school sweethearts. We like get kind of confused because when we started the program, we were no longer technically high school students, but we kind of still were because we were enrolled at the university full time.
You were
Right?
science sweethearts.
Yeah.
Yeah, you need to make your own term for that. Like, oh, were you high school sweethearts? No, we were pre-college sweethearts.
No, actually, we were pre-college sweethearts.
Pre-college sweethearts. Yeah, but I don't know, because like we were in the same classrooms and lecture rooms with all the other university students. So that was a unique take, right? So my junior and senior year, I finished within the university, right? So I got high school credit for university courses. Usually most programs are the other way around, right? So you usually get the university credit for the high school courses. I mean, you get the university credit for high school courses, but here, like, we were all in, right? And yeah, so like once we were there, probably the second week, the first week, you know, getting used to stuff. The second week we were there, one of my friends came back in to like that we had like a homeroom, and he's like, yeah, I just finished declaring my major. I'm like, what? Like there's a thing you can do to declare your major. And I'm like, all right, I gotta go. Where is this place? And I went directly to the then I'm not sure what the specific like College of Science, you know, room was then, but I went there, and I'm like, all right, I want to declare my major, physics. Are you sure? And I'm like, yeah, why not? Okay, just saying. And that's usually the reaction I get now, and probably you too, Richard, when you tell people you're studying physics. It's something that I you know, I really want to work, you know, just chisel away at that reaction from people. So like now when you tell them you're studying physics, they'll, rather than being like scared, they'll be like, oh wow, that's so cool, tell me more.
If you put astro in front of physicists, then they'll want to talk to
Yeah.
you.
Oh, okay. I maybe I should practice doing that. Astrophysics. Yeah. Yeah. And so then that puts me into college, right? So I my parents, right? Oh, here it is. That's why. I didn't know why I brought up my parents, but yeah. So I had made a promise to them very early on that I wouldn't I didn't want that, and this was actually something that I told myself. I didn't actually. Maybe I might have told my mom, you know, but like a promise that I kept to myself was that I would do my best so they would not have to pay anything towards my college education, right? So like I wanted to do my best. I knew that there was programs, right, that help with this. I knew that there was things that existed with to help financially, and at the time, like my mom wasn't working at all. So like she would take care of us. I have an older brother, a younger sister, and so like she decided she chose to be mostly a stay-at-home mom, and my dad would be out of town, right? So I guess that doesn't leave much of a choice for my mom, you know, to whether or not to be a stay-at-home mom or not. But I mean, this is a reality for a lot of people, right? So like dad goes out to work. My dad would work out of town, so he'd be gone for long periods of time from the house. So it would be, and sometimes he would be working in different states for long periods of time to bring in some income, right? And so we would usually be floating around with our income. It wasn't something that was too stable, right? And so that was one of the largest motivators for me to not ask of my parents financially. And luckily, like as these opportunities came up, I've been able to take advantage of these opportunities. So pretty early on, I was always hanging around the physics department, and I was asked at some point, like, just I would literally hang out by the office and just talk to the people that were there. I was that guy. And yeah, and actually I don't I remember there's a guy that would always tell me, like he would pass by and be like, what are you doing here? Like, you should just get yourself an office, uh, but yeah, I would be there so often. That's pretty much it. But at some point, I learned that there was like an opening for student position to work within the department. I'm like, oh sure, let me take that. And so I want to do physics. Now I'm working for the department. Like, this is all cool. And so I like it. Again, this is like, I took advantage of any opportunity that I had. So this gave me this opened my eyes into the world of just academia and how things function for an institution, right? For physics in general, right? So this is pretty cool. This is pretty cool. And then I was offered an opportunity, not just like sorting 4 years of grants receipts into the different grant folders, which is a point of a point of pride for us, right, in our department, that we actually had those massive grants, and that it was being used appropriately. But people had to keep track of all these things, and so I got to sort through all the the receipts and put them in order by date.
Had to be done.
It had to be done. Yes, it had to be done, right, for the greater good.
That's right.
But anywho, like that, I was finally, like, I was offered once, I reached a higher level in my physics studies, a position within one of the research groups, which is the Center for Gravitational Wave Astronomy. And so I pretty much, that's been my home for quite a while now. And that's been my home for quite a while now, and that's under Mario Diaz, right? And he's an awesome guy, and spearheading so many like large projects, and so I in this work of administrative type stuff, like I got to see a lot of essentially what people don't see, like the and this is for just like all of us, like for the physics department, and also the for the center, right, for CGWA specifically, the analogy, right, of the duck float, like it looks like it's flowing very steady, but underneath you see the little feet going. There's so much that actually happens. And as lab manager, I like, I was there. There was our institution was made up of then UTB was actually UTB TSC, so it was a combination of which is the Texas Southmost College, which still exists. It's a community college for in the Brownsville area, and right downtown, which is pretty neat. It's really cool. And the campus itself, is a street that divides UTRGV and UT or TSC, right? Because it was all
campus.
That's what I was gonna say. It's a beautiful,
Oh,
beautiful campus. Yeah. No. I mean, it's perfect, right? Because like you got to experience it too. Like I've seen it. Every year I would go with my parents to like Charro days downtown, and so we would see all the festivities, and every time we would go to the parade. So like that's something that I would see frequently. Growing up, I didn't know that that's what I was looking at up until I started going to college there, right? But the but you hadn't seen it ever until you came here, right? At least your first time.
Yeah, and you saw, I mean, I was going to ask you, did you take classes in any of the buildings in T? Because they were doing that at the time on the TSC campus. I didn't have that perspective, but I probably would take almost daily, nightly walks through that campus. It's so beautiful, like especially by the Versaka.
Yeah.
But you took classes, right?
Right. Yeah, so I did, just because the distribution of classrooms was all concentrated on that side, right? So like, and which was the it was the college first, right? Then it became the university and college. It was essentially like a satellite campus for the university, and then the university then started growing, and the number of programs started growing, and then there was a rift that happened where there was a separation between the community college and the university. And during that rift, I was I was the lab manager during that time. So mind you, I was still an undergraduate student as well, but I probably mature enough to handle it. So at least that's what I hope, and that's the reason why I was there. But yeah, it was very intense negotiations that were happening on their end in terms of administrative things. So I got to see at least a little bit of that, and I got to live through it. So it was something that definitely added to me as a person, like who I am, because of that, right? So I got to see the different layers that an institution actually, of how an institution actually functions, at the university level, which I think is really important to know as someone who, like, if you want to be in academia, I think you should be aware of the layers that an institution actually is. Yeah.
Right. And Mario would keep us very close to the process too. I remember
Yeah.
he would like almost bring us over at various points along our time there and be like, "Hey, just I'm showing you there's something that's happening that you rarely get to see from this perspective.
Mhm.
This is important for you to know." And he did that a lot. It's very valuable insight. And it
Right.
sounds like in academia you could do anything. It sounds like almost like simply you could do anything you want, like in terms of research. There's that freedom of research, but it comes with all that other cost, as you say.
Yeah, exactly. And so yeah. So that pretty much places me now probably around 2013. So uh so we're close. We're close to coming home, and by home I mean today, right now. And yeah.
Yeah, I was going to say, I think it applies to a lot more than that too. I mean, in the business world, I've been told before, like, oh yeah, no matter how well put together a company seems, like it's always in the background crazy. And like your analogy of the duck, and that's kind of how it is for. I mean, some do a better job than others at making it look good on the outside, but no matter what, I think almost every organization trying to do anything and trying to be better is scrambling in the background to do so.
Right. For all the band geeks and band nerds that or anyone who is currently in a band, you're probably familiar. Like I look at the shows that people put on, and like for concerts, and there's so much that happens just for, like here right now I'm in my square, right? And so this is what I'm projecting out into the world, and this is the exact same thing that's done for any performance, a live performance, whether it be theater, whether it be music. But like I got a taste of it like growing up doing band, right? And like you're not in very pleasant places before, like moments before you go onto the stage. There's so much, like a lot of stuff, right, that people don't see. And so it's but all that's like um I think it might have even been like a Lady Gaga show. Like I saw it on on the TV. She's like completely glamorous, right? The show is like over the top, amazing, but moments leading up to that, like the room, that like the dressing room, it's a locker room. Like it's not that great. And they're walking in this very gray, bare hallway. There's like, random equipment everywhere that might not even be for the show specifically. And then finally, boom, on stage. And and yeah, and sorry, but
And
that's
then it lasts for a few minutes and they're back in the locker room.
and back in the locker room. Yeah. And that's exactly it, right? So like for organizations, and I guess that's true, I hadn't even thought of that, but for businesses, I can see that being true as well. There's a lot that happens in the background, for things to be successful, right? Yeah.
I think it almost sounds depressing, but it's not. I think it's just it's a side effect of ambition. You don't want to get comfortable, and that's that. Like I really like what you said about when you mentioned you're a physicist and people are like, why? It's like because it's not easy. I mean, because they know right away that that's not an easy thing. That you suffered a lot and are. I mean, like Richard's still suffering. And it's a hard thing to put yourself through. And so it's like a lot of people are like, why would you do that to yourself? And the truth, well, because you're ambitious. And just like any organization or company that wants to do better, it's not enough to get one grant or do one good performance. As soon as you get off that stage or you get the degree or you get to that next level, you're like, all right, not going to bask in this, just going to keep moving forward. And so yeah, I had to put a non-depressing spin on it.
Yeah. No, yeah, that's definitely true, and ultimately that is what happened. Segue back to the story. That is what happened with the with the labs. Like I have this like I have this knack, right, of doing stuff with my hands. Like I like to do stuff, and I like to see. Yeah, I'm a tinker, right? So that's that's my
Hey, what do
classification.
you do?
Stuff. Yeah. And the yeah, but really, like I like to do stuff, and so this lends itself really nicely, just like we're doing experiments for physics. And so meanwhile, I was also lab manager. I got to test out like doing physics demos, right? So like doing physics demonstrations, and sometimes I got to try things out for myself, which was something that was pretty cool. Like I would grab some of the equipment that was there in the lab and string stuff together. And whenever I got something working that was really fascinating, I would open the door, look outside, and see if anyone was around. Like, here, come and look at this. And I remember showing one of the demos to a professor, and he's like, "Wow, like this is really cool." The yeah, that demo in particular was talking about coupling two pendulums. And so like I had two pendulums equal length, equal mass, and I would hold one still, let go of it, pull one back, and then let it go. It starts swinging, and these two pendulums were attached on a string, so it was allowed to give just a little bit. There was enough vibration that would go through that it would start wiggling the other pendulum that was originally still, and it would begin to resonate. And it would get to a point that all the energy from one seemed to get transferred into the other one. And so the original one that I had picked up and let go is completely still, and the other one is swinging back and forth. And it's just so mind blowing. Like that kind of stuff is like, why? And when I get it to work, right? That I think that's probably my drive, like, to keep on going. And that's one of my things, right? It's not red, like this is my mission in life. Like my mission statement is to help curious minds grow curiouser. That is my personal mission statement. And so when I figure stuff out like that, like I want to share it with everybody. And so that's why the labs were something that were so meaningful to me. And just like everyone having a good lab experience was something that was essentially personal for me, right? Even as an undergrad, like I got a really deep appreciation for the activities that we were doing, and the intention that was made when those labs were first created. And so like anytime there would be any kind of failure, I would be like, all right, let me think about it. All right, I think I have a fix, so we can keep that intention working for moving forward. And so like after the split with UTB and then TSC, then UTRGV came around and was established as the university institution that we are now, right? And so I started grad school 2012, right? So I graduated with my physics bachelor's degree, and I started grad school, and yeah, I was at one point working on a different project that wasn't astronomy. It was more materials related, and there was this big project, the observatory. Then it was called Nompuewenu Observatory, and it was sitting at the Brownsville campus of UTRGV. At that point, let me think about it. 4, 5. So at that point, I don't think it was there anymore. I'm not sure. Richard, when was it that you came on over to campus?
I came like when I moved to campus or when I moved to Brownsville. 2016. It was gone by then. I think it got moved. It was there like in 2013, and then it got moved in 2014.
It was 2012 when I think the thing happened. So one of the
real quick, I've always been curious because I've never even known where exactly at UTB was the observatory.
Right by my apartment.
Oh, really?
Yeah.
Huh. It was
behind the rec center. So there's a street where the rec center is, and where the apartments are.
Yes.
And drive down that street, and you keep on driving down that street. Don't turn into the parking lot for the rec center. Like, you just keep on driving down that street. There is the old, I'm not even sure what it is, like some naval office, or I think it used to be the where the National Guard was, for Texas. And on now there's a school that's there. So you'll see Beck's, the Brownsville Early College High School, right there. And there, I think it's still there, the concrete pad where the dome was. So you should see like this big concrete pad there by itself.
That's a memorial.
Wow.
Was that a memorial? Yeah, we should.
Yeah.
That should be.
Should designate it as a historic memorial.
Yeah.
We could also use it as an example of dark sky pollution. Be like, this is what happens when.
Yeah.
Just an empty slab of concrete. Are you happy?
Don't let your observatory become a slab.
That's funny, because I mean, it would probably be a really good poster because you can see the floodlights, like. Yeah. I mean, it's important to keep the buildings safe too, right? So.
That's true.
Right. So, but right, we should be somewhat responsible with our lightings.
Somewhat responsible, or switch to infrared cameras for your.
Well, I don't know. I don't know if that would help for observations any. Right.
That's true.
But yeah, that's just sensitivity, right? IR with the cameras.
Infrared with a telescope.
Yeah.
You're talking about. No. Yeah, I thought you meant for security.
Yeah. Oh, yeah, that would work too, right? Yeah. And so 2012 started grad school, and I was teaching labs. No longer in my role as lab manager, right? Since we became UTRGV, we were larger, just suddenly larger institution, right? Including we are now, as we are now, right? So we are an Edinburgh campus, a Brownsville campus. We now have a medical school based in Harlingen. And we have many labs and different just facilities spread throughout the Rio Grande Valley. So cool. It's great stuff, right? So like wherever we have a clinic right? So like there's a fully functional clinic in one of the areas that is on the outskirts, I think, of McAllen. I'm not exactly sure where exactly the clinic is, but I think that's really cool, right? Because it's giving back to the community. And yeah, so I was working on a different project, and Mario tells me, all right, Moises, I need your help to make sure that this project gets done. And so at this point, we're fast forwarding to um, 2016. So the observatory, just like the quick run, is that the observatory was dismantled and it sat in storage for about 4 years before, even though it already had a resting spot, or like its current location now. It was already decided since then where it was going to be, but there was, again, these logistical hurdles and layers of institution that had to go. But not, and I don't mean just on our side. I also mean, all parties involved, which is Texas Parks and Wildlife. But I think probably even City of Brownsville might have had to do a part with this too, especially since we were moving these large pieces of equipment from one side of town to out of to the edge of town, right? So there was a lot of logistical things. And then I when I came into the group, the observatory was just a shell. So like the structure itself was up, but everything needed to be put in place. So I've probably touched a lot of the observatory, right? Already by this point. Yeah, and I've functioned as Richard said in the introduction, as engineer, though not I do want to be like give justice to all the engineers. I'm not like a state certified engineer. I don't have formal. I'm not an engineer by trade. It's just in practice, essentially, with the necessities of the things that need to happen in the.
You just do stuff with your hands.
We just do stuff with my hands, yeah. Yeah. And yeah, so like setting up the telescope, getting the pier in its place, making sure the basic things, making sure that the observatory shuts completely. One of the things that one of the earliest problems, I was looking back at some pictures, we see that there was probably, like, when they made the concrete pad, it was made to be the exact shape of the dome, but anyone who works with round observatories knows they're all eggs, right? So we know they don't necessarily sustain their perfect circular shape. So you should, if you're thinking about making your own observatory, take that into consideration. So the doors were outside of that, like, radius of the of the concrete pad. So there was like a 3-inch gap underneath. And I mean, one of the things you want to be careful with is just like dust, right? So like we are in a dusty area. There's a lot of wind that kicks up here in South Texas. And so that was going to be a big problem. That was going to be a really big problem. So I got a hammer drill. I made some holes in the concrete, put some rebar, laid some concrete. I filled in that spot. And yeah, Walton was there to see this happen, actually. So we have some
Hey, Walton.
yeah, we have some pictures together from those times. And then that's when I met Richard. 2016. Yes. So we're the beginning of the observatory, which was then in 2018. Is that correct? I'm getting my years mixed up now. For
No, it's okay. Everything, just shift everything back. Like, so it's like 2015 was when there was a shell,
yeah.
and then 2016, I think by that summer it was like complete, because that's when Carlos and Raul were there,
Exactly.
and they calibrated the telescope. It saw first light in October of 2016. Then I got invited by Mario in November 2016, and then from then on, I think 2018 or 2019 was when so 2019 was when we upgraded optics, right? We went from 16 to 17.
Yeah. And
think.
so,
Okay.
yeah, I mean, then we did the inauguration, right, where we renamed the dome, or not the dome, but the observatory itself to the Dr. Cristina Torres Astronomical Memorial Observatory. Yeah.
Yeah.
I think I got the order wrong.
I'm
I
so
heard,
used to calling it CTMO.
me too.
So.
And so I'm sorry. So yeah. So the Dr. Cristina Torres
Memorial Astronomical Observatory. It's Memorial Astronomical.
Memorial
Because I
Astronomical
remember it
Observatory.
ending in Mao.
Mao.
Like when
You're
when
right.
we were going through, like
Yeah.
I remember when we renamed it, we had that kind of quick meeting, like, okay, what are we going to call the acronym? Because we're astronomers, and
Because we're
it has to be an acronym.
Yeah. Yes. And but essentially, like, Christina was a mentor of mine, and just the upbringing of this nurturing curiosity in others, right? And yeah, so like that's essentially the whole point of our observatory, is being part of the community, and still nurturing this curiosity that we are all born with. Mm-hmm.
That's all I've ever seen there, working there, and meeting so many students and teaching people and learning from people, and all the different things that the observatory went through during my time there. Working with you, I've seen that entirely. Yeah. The one thing I wanted to ask, I don't know if there's a good way to just go into different things. We're going into so many different topics, so I mean,
No, this is fine. This is what we're here for.
right. So I guess I'll ask a kind of an interesting question: is how do you farm telescopes? How do you farm telescopes?
How do you farm telescopes? Well, we use the traditional method, like as in Minecraft. First, you have to till, a couple blocks. Yeah. And you have to mine the creepers, and
I'm so glad you made okay. So I have to say also that Moises makes the best sound effects, and it wasn't random that I picked that he's a good travel partner, because literally on a 12-hour car ride, it'll never be quiet. There'll always be some sort of beat or sound happening. So
yeah.
There's something about your vocal cords that just.
Well, you should tell the story, Moises, about how you spooked me early on in the observatory, remember? Because you were able to
I need to make sure I'm hydrated for this. Well, actually, I'm not sure which sound anymore.
I don't remember, but he basically, there's like the acoustics in the observatory. He could make it sound like it came from outside the building, and it sounded like an animal. And he's like, "Did you hear that?" Yeah. Actually, Moises had a great teaching strategy for me. Every time I would be learning how to do something, he would just his eyes would get big suddenly, or he would just be like, "You sure?" Even if it was right or wrong. It was a good learning device. Oh,
Get people to question themselves.
Yeah.
Am I sure?
Yeah.
What am I doing here?
I think that's probably this is one of the teaching strategies or techniques that you can use, is shake someone to their core, make them doubt themselves internally, and if internally they can win that conflict, then you know that they learned it.
Cause existential crisis, overcome existential crisis. It's there for good.
No,
that or have a noodle. Remember the noodle?
Oh, the noodle.
Also
right.
a good. We don't condone corporal punishment, but we do have a pool noodle, and it's been used for teaching experiences. Let's
yeah. Yeah, but the noodle. The yeah, so farming for telescopes, we We actually had to do something similar to that. Well, the area where we're at floods, so that's something like for people that aren't aware of, you know, where we're at. We sit in a delta, like that
Yeah.
is, like where I'm at now. Probably years ago was part of a river at some point, right? So, and that's just the nature of the river delta areas. And so when there are those few instances where sometimes it could be as often as once every year, you know. So like it's not uncommon that one day just suddenly, like, oh, it's a nice morning out today, and you know, it just pours continuously for 30 minutes, and then it becomes a beautiful day again. That moment everything is flooded. And so, um and yeah, I mean, and there are some areas around here where the infrastructure is not so great, so the water stays there for a long time, and that's not so good. And we are susceptible to hurricanes here as well. So every once in a while, we'll get some of those armbands from the hurricanes as they make their way through either the south. We've been pretty fortunate that we haven't had one hit us directly, but I mean, it doesn't matter where you're at in terms of the area of any of the part of that weather system. It could be pretty bad. It doesn't matter if it hits directly or if the eye hits directly or not. And so, we that's just part of the nature of living in the Gulf Coast. You know, like this is the reality of it. And the it has flooded. And I remember one time that it rained. We have a storage container that is like one of those shipping containers, that like those metal ones you open up.
Area 51.
Area 51. No. the the so the oh, I think I'm frozen right now.
I can hear you. Just everything's fine for
I
me.
think I'm frozen now, and I'm not sure if you guys can hear me or not. Let me see.
I can hear you.
Make any... Okay, perfect. Okay.
Yeah, we can. Yeah, it's like nothing happened.
Like nothing
Maybe there was some audio delay or something.
Okay. So, right. So we have those storage containers, or we have a storage container. We don't have multiple. Like we just have that one, and it had flooded. Like it rained really hard, and I remember when I drove to the park, I went to go check just to make sure that, like, okay, the equipment was dry. And I remember at that point, some of the water had already receded, but I can see the water line above, like the opening of where the doors actually are. So luckily, everything inside there stayed dry. Right, that's how they make those shipping containers.
Wow.
And the dome itself sits on a concrete pad that was intentionally like higher than the rest of the ground, but at that time the rest of the ground was like really low. So one of the things that we did is we had some pavers installed, but before they put the pavers, they put like they raised the level ever so slightly, so it wouldn't succumb to flooding, or at least not nearly as much. And then we had concrete pads installed that were at the same height to where the dome was, like the big dome. And now I'm using particular language here where I say big dome because we have these. What's also necessary to have a farm is you need mini domes to host your other to host your other dome or your other telescopes. And inside each of these mini domes will reside a telescope. So this is one of the projects that we're currently working on, is getting the telescopes communicating to the internet. So we have like the latest scoop is that we actually have one that has like the dome, like all the domes are there, and by all I mean we have 9. Let me count them real quick. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it should be 9. We have 9. Yeah. Mini domes, and of those 9, there are 3 telescopes sitting in 3 of those 9. So we have guests apparently.
Contribution to the conversation.
That's right. they are barking in agreement. Yeah, so they agree.
They were like 9, dude. It's 9.
It's 9. It's 9. Okay.
Wait,
but,
so
yeah.
there's 3 sorry to interrupt. There's 3 telescopes currently installed?
Yeah. So they're not completely set up yet. So none of them has seen first light, but we're so close.
Which ones are they?
Get the guess.
Yeah. So we have.
It's like one of those you're moving the cups. And
I'm over here like,
which one is the telescope in?
Carry the 2, divide by 4.
So if I remember correctly, we have some 12-inch Meade telescopes, and so those are the ones that are in there now. Mm-hmm.
Awesome.
Yeah.
Awesome. Yeah, and the 16-inch will be installed at some point too in one of them, hopefully.
Yes. Yeah, and that one actually might be installed sooner than later. We one of the issues with that one is just that it's so big.
Yeah, it's heavy.
Yeah, I was gonna say, is that gonna wait, like big, like it's hard to put in there, or big, like the mechanics of it moving around in there won't work?
Yes.
All of the above.
Yeah, so that was one of the challenges, is the manufacturer where we got our piers from, the thing that holds the telescope up, has mounts already designed for different telescopes, right? So they're adapter mounts that will then hold like all your equipment up. And there was a miscommunication that happened, and when we told him, like, we have a Meade LX200 telescope, and he's like, all right, here you go. The thing is that the 16-inch Meade LX200 is a different beast. Yeah, so that's it's massive, it's huge. And so, like, if you were to look at the tripod that comes with the LX200 system, the 16-inch specifically, like, this is like massive, thick, yeah, thick. And each leg of the tripod's like this big. The platform, like, that you put the mount on for that is just like a chunk of metal. Like, it's huge.
Right.
And it has handles on it, so like multiple people can carry it. And yeah, the thing's heavy. And so we had to ask for the correct mount, or like mount adapter for that. And so that was produced in Poland and then shipped to us.
Oh wow.
Yeah. And so that was a surprise. We didn't know. And finally we got it. And so that's why we have it now. So
awesome.
This is, yeah, that means that it's possible. It's possible to be installed sooner than later. And but that's essentially it. Each of those domes requires data. Each of those domes, a data line and a power line. So the funny thing is that all the equipment runs on 12 volts. It's meant to be portable. So it's all low voltage stuff going into each of these domes.
Just carry your own power grid.
Right. Like, actually,
I don't see the problem. Just portable generators. Take that to an event.
Some solar panels and some chargeable batteries.
Yeah. Hopefully in the future.
Yeah.
Mm-hmm.
I know Moises and I have speculated about different things we could have at the observatory, like a weather station, etc. And solar panels have come up multiple times. Photovoltaics.
Mm-hmm.
They could be good for student projects.
Yeah.
Now, students will be able to use these mini domes, right? And they're supposed to be remote controllable.
Exactly. So one of the many hats that I wear is that of a part-time instructor for the astronomy labs. So part-time lecturer, I think, is, if you look up my email at the university, it comes out as saying part-time lecturer.
That's the title.
Yeah, that is the title. And and which is pretty cool. I oversee this semester. I'm overseeing 5 labs, and so each lab has over 50 students, just about, and it's a pretty unique just learning environment, right? Because we're doing it over the just like this video call, right?
Mhm.
And yeah, myself along with Americo Nojosa. He's been the one who's been along with me this semester and the previous semester working on designing these instructional labs. Right, there was a team early on that started before I joined in this effort, specifically in formal education, for this we call it the new method in teaching astronomy labs, and that was Alan Hendrick and Eric Valladino
Hey,
and Walter
everybody.
Matre. Hello. I'm dropping names, and that's because I think that they did a lot of work, beforehand, and I think they should also be recognized. The cool thing about Eric and Alan, uh, they are my friends and colleagues, right? They are my colleagues, but a lot of people might recognize them as Mr. Hendrick and Mr. Vallarino because they are teachers at our high schools, and so. Teachers at San Benito High School and at Veteran Memorial High School, and so this is actually something really cool that they helped do, and it fits perfectly in like this workflow that we're trying to do, where we're trying to make essentially astronomy accessible to everyone, and in that is exactly that the students in our astronomy lab, we're essentially teaching them how to become observational modern day, and this is careful with words. This is what I tell my students all the time. You got to be careful with words. And a modern day observational astronomer. Modern day observational astronomer. Yeah, just because now we use computers to look at stuff and take data and all this, and so um, there are typically 11 labs during a semester, and by the end of lab 6, they have done a connection to a simulated telescope and like a simulated observatory, essentially,
Mhm.
telescope and CCD, where they like use the go-to commands on the simulator using this program, and take some initial data, and they even look at the simulated FITS files that come off of that simulation and do just a basic visual analysis.
That's really interesting. And so from that simulation, they learned the overall concepts of like, so the modern observational astronomy is like with CCD cameras, digital images, and do they go into like different astrophysical phenomena? Like, or are you doing one particular object, like type of object?
So right now, no, actually, like we try to cover. Oh, right. So just to put things in context, this is intro to astronomy 1.
Mhm.
So this is the lab that complements the class, and so in it, what we're doing is actually trying. Like the idea is that we learn astronomy by doing astronomy the way that astronomers do. That's the catchphrase that I use. Yeah,
I
for
feel like
this.
you could fit one last astronomy in there. The way
Yeah.
astronomers do astronomy, just to say it like 5 times.
So, subtitle: "Roughing It as an Astronomer."
Yeah. um yeah, and the idea is like first we need to catch them up to modern times, right? So like that's why we spend the first 5 labs in developing this conceptual like um roadmap to get us to modern day astronomy, right? The first lab starts off with this whole concept of spatial recognition of what it means to like look at a star, right? And the coordinates that we use to do that. That's actually, early on, I hear people saying right ascension declination. From when I started physics, there was that group, the the ARC group, the Irreceivable Remote Command Center, that like I was friends with, and I got to do a remote observation one night. My not by myself, but like I attended one of these observations, and I would see right ascension declination, hear people talk about it. I'm like, what even is this? And and that's how we look at stuff in the night sky, or actually not even in the night sky. This is how we point stuff out in space from Earth, right? And we get this spatial recognition. We get this concept of, okay, I want to look at things through the atmosphere. What are things that I need to keep in mind, right? So like, my observatory is here, like for example, in the valley. So there's a lot of humidity. All right. I need to take into consideration the cloud coverage. March for us, we get a lot of clouds during this time. I'm curious, how is it over there, Richard?
Lately, it's been actually pretty overcast.
Yeah.
And I was looking over here because I have a tornado warning right now. So first one, but anyway,
Okay.
this just did. Yeah, so it's been cloudy and windy here.
Oh, okay.
Yeah.
Okay. Yeah. And the
like other effects, like atmospheric effects, right? Or
yeah, exactly. And so we have to, like, we tell people, like, essentially having themselves question, why do we do certain things, right? So like, what are the effects if we were to do it other ways? So like, one of the questions is, why do observatories usually pick desertic places? Why do they pick places with really high altitude? And then we get to show them a picture of the Toros telescope, the the project that UTRGV is spearheading in Argentina.
Ooh.
Yeah. Ooh.
Yeah, it looks like Mars up there.
Yes. Yeah. It's very dry.
Yeah.
And windy and cold apparently. So
Yeah, isn't it the driest place in the world?
yeah.
And I think it has the best measured seeing conditions. So I'll let Moises at some point explain what seeing is, but basically the smaller that is, the better, and it has like the best seeing in the world for astronomers.
Yeah. The yeah, well, I said Toros, but it actually, as Richard said, it's like astronomers with their acronyms. It's the transient
because
optical
there's also
robotic. Yeah,
sorry, I did not mean to interrupt in the middle of the acronym. That
Whoa,
felt like
whoa.
like a sin.
You're good.
I was going to say, no, yeah, especially here because there's actually a soccer team called Toros.
Oh yeah, that's true. The Toros FC, right? So we
yeah
the football club, right? So just putting it out there.
Right.
Yeah, they're cool. Right, Toros is the Transient Optical Robotic Observatory of the South. I had to practice that line so many times because we were going to do a public presentation at one point where they're like, all right, Moises, you are MC. Okay, you have to make sure you introduce Toros to the public. Okay, what is Toros? And I would slip up so many times trying to get through those words.
It never hit me until right now, but being an MC is so natural to you that it's literally your initials. And I'm sure you've heard that before. I'm sure I'm not the first person that said that.
These are my complete initials. I was born to do this.
MC is MC.
Yeah, there's no middle name or second last name. It's only MC.
I mean,
just
to
walk
be
up
honest,
anywhere with the stage and grab the mic, and people are like, "What are you doing?"
Yeah.
Just like what I was born to do.
He does have the best "ladies and gentlemen" I've ever
Ladies and gentlemen.
Yeah, I had to pull up. I recently had to use iMovie again to do a video, and I listened again to the Star Wars one that you narrated, and it's so great.
Oh, it's so good with the was there like Star Wars music playing too?
Yeah, your voice
so
on top of Star Wars music is just like nothing more natural.
Yeah.
Which Jedi's lightsaber?
I don't know. I wanna redo that. Just go through that trivia again. Like, because more recently, I like restarted my entire learning of Star Wars. right? So like this at least in terms of visual media, that's this has been like the longest binge of Star Wars, so it was pretty cool.
Well, that was for May the 4th last year, and May the 4th is coming up. So
Oh yeah.
maybe we should start thinking of some Star Wars thing to do.
Yeah.
Like, I don't know if we're even allowed to like watch them online, and people probably not, but
Yeah,
I
no.
would just like to. I would like to marathon Star Wars during that time. Usually, that's something I like to
Just
do.
host like a 10-hour event where we watch one movie, but like every minute you pause it and explain the science of what just happened.
So it's not a 10-hour event. It would be like a week-long event. Like, actually, this laser bolt was removed in the new version.
1 week per movie.
It can be like the commentators, right? So we'll just be there and
yeah. Oh my
well,
god.
what do you think about this? You know, and just to be like, you can be there like while like there's like maybe a main timestamp so everyone keeps track of where they're at in the movie, but like we're just here talking about it while it's playing.
Yeah, we just have like the Zoom room open and be like, so did Han shoot first in that scene? What do you think? Send us your like. You could even do a YouTube live stream of that, so then people can submit questions, and we could actually do like. Could we actually do that as a thing, maybe as a Stars event, like a May the 4th event? We are the content team. I mean, Brina should be here too.
That's true. Yeah,
I think so. Yeah.
Yeah, I
I've
mean,
been looking into Zoom
that
webinar. It's possible.
Oh, cool.
Yeah. So yeah, the just
The new way of teaching astronomy.
the new way.
I know.
Yeah, but yeah.
So you talked about the mini domes and the equipment that's going there, but it's something that kind of comes up a lot is the main dome, the CTMO. Can you explain a little bit of the setup in there right now?
The setup in there right now. So right now, this is the upgrade, right, that Richard was talking about, that we have now the 17-inch, what we refer to in short words as a CDK. It's a telescope that was made. Well, actually, being very particular with the words, is an astrograph created by actually it's an astrograph made by plane wave instruments, and it is very nice. It works so smooth compared to my prior experience of the telescopes. The mount that the 17-inch telescope sits on. Also, just for some added context, right? Because there might be people who aren't aware to what does that mean. I'm saying 17-inch, and when we said 16-inch earlier, that's the diameter of the mirror that reflects the light or that collects the light that in the telescope that we're using. So you'll hear people talking about meter class telescopes, and so like those are huge, right? Those telescopes are at least 1 meter in diameter, and the one that we're using right now is 17 inches in diameter, and it has an open truss design, so it looks really cool whenever the shroud's not on there. Like you can see like the cool like carbon fiber trusses, and the mount that it's sitting on is an L-type mount. It's the L500. They call it the direct drive because those motors are, if I remember correctly, I think they're, and maybe the the engineers from Plane Wave, if they hear this, are like, this guy, what is he saying?
Don't at me.
yeah, don't at me. These direct drives are super smooth. Like they work so well, especially after tuning. Like it's able to. The technical specs, they said something that it can move something like, I don't know I don't know if you remember, Richard, something like 50 degrees or something per second. I don't know, something really ridiculous. So like it can like Wow.
It can
Like,
track satellites. Like you can give it like the projected or the predicted ephemeris of of a passing satellite, like the ISS or something, and it would be able to track it. So you can, like, normally telescopes. Well, I don't want to say normally. See, I should be careful with my words. The telescope that the observatory uses tracks sidereally, so like it'll follow this something in the sky the way the celestial sphere rotates conceptually. But you can redirect it to look at proper motion objects like asteroids moving overhead in different directions, etc. So, could you also specify what CDK stands for? Do you remember?
so the it's actually initials for something that actually I never explored too deeply into, so I don't know.
Yeah.
But I think you know.
Yeah, I was just trying. I just wanted to. I prefer you to answer questions because you're the guest, but that's a corrected doll, Kirkham. And basically, what that means is you have two mirrors. Most reflectors have two mirrors, a primary and then a secondary, and they can be different shapes. So this one has a flat shape primary, and the secondary is hyperbolic or parabolic, and I forget exactly what it is. But it's a weird shape secondary, which cancels like what we would call aberration effects. So um, a classic example is like when light passes through a prism, the light splits into component parts. And through a telescope with glass, like a refractor, you would see that in certain targets. You would see this chromatic aberration. So you can cancel stuff like that with the different shapes of the mirrors. And so the one at CTMO has a very special secondary mirror shape. So
Yeah.
bingo.
And yeah, cool. Thank you. Thank you for teaching us. Yeah. Uh, then what else? Okay, so that's the telescope itself. The dome is huge. Like the dome is actually like unnecessarily
Obscenely
large.
big.
Yeah, so like our dome could actually handle, a really large telescope. Like it is possible to put
Meter
like
class?
Yes.
yeah. Mhm.
Yeah. It could
Yeah.
hold something double its aperture. It could do like a 35-inch telescope, no problem.
Wow.
Yeah.
And so why do we have such a large telescope? It's so we can invite people in, and that's actually it. And so we have that floor space, so we could so we can have people in there. Of course, it's been very sad for us that we haven't been able to have people in there just because of the limitations and the restrictions that we had with COVID. But it seems like we are almost able to see the light at the end of that tunnel. So this is good for us. But the aside from that, we also have we have we're working on a control room, right? So like in the north, or where it gets cold, like for real. I think they call them warm boxes, right?
Warm rooms.
A warm room, yeah. So and again, like I live here in the south, and I've been here all my life, and so I don't know what it means to be really cold. Well, I mean, now I do, at least a little bit, right? So I think all of Texas does now.
Everybody learned
But
it that.
yeah, so that was oh man, and that was pretty intense. And I didn't go see the dome that day. There was that one time that it snowed. I did go for the snow day, but I didn't go this time around when we had the freeze. And something that I messaged Americo, telling him, Americo's like the operations manager for hi.
Hey, Medical.
Yeah, I messaged him and I told him the dome right now is probably frozen shut. Like, this is something that we've never had to deal with before. But I mean, it was overcast the entire time anyways, so we weren't, there was no way that observers, even if they wanted to do an observation in the freezing cold, because we don't have a complete control room just yet, they would have not been warm, right? So they probably wouldn't have been able to open the dome. Yeah, so that's one of the new things, and we had some like equipment racks donated to us by one of our friends from the community, and we.
Hi, Dave.
Hi, Dave.
Hey, Dave.
Yeah, he's
Man,
really
so
cool.
many shout outs. This is so cool.
Yeah. Well, you know, and this is the thing with our observatory and our group, like it's not just one person, you know, like this is truly like a community thing, and I love it. You know, it's great having so many people helping out with different stuff, and yeah, so there's a lot of the equipment racks that are just kind of like sitting like statues inside the observatory, just because since the start of the pandemic, we acquired these just before things were beginning to enter lockdown, right? And so like we were trying to be very cautious with the amount of people that were gathering and moving these things. And so like while we were doing moving these things, like we're all in masks and this, and they're made from steel. Like these things are heavy duty stuff, and so they've kind of just
Didn't it? Oh, it rained really bad the day that we picked
was-
it up.
yeah.
We picked them up.
Yeah, you remember.
We're slipping on the U-Haul and stuff.
Yeah,
That was rough.
For the record, I was not there, but I saw pictures of it, and I was like, that. I could tell. I was like, that looks brutal. Like I could tell. Good job, guys.
Yeah,
Good job.
Victor was there helping move stuff. So doing the heavy lifting, and this is quite literal. These things are heavy, and so but yeah, so they're sitting in there but we have plans for them, right? So like one of the things that we're doing is we plan on setting up these equipment racks inside of this control room, and to serve as well. One is the control for the observatory itself, but the other thing is also for essentially just like a status of the site, right? So like we want to see because we have that farm, right, that telescope farm, which will at some point have the fully 9 fully functional like mini observatories, right? Each dome with its own telescope and equipment that needs to be maintained, right? And so that will have some status monitor for that. Also, you know, status monitor for whatever technician would be operating the telescope for that night. We're moving, which is really awesome. You know, like I know early on when like we had just had the observatory installed, and Richard and I were you know, just talking about potential things in the future. I said, let's automate this thing. And I remember Martin was Martin.
Hey, Martin.
Dr. Bedois, right? So then he's like, "Are you crazy?" Yeah.
And I think we were just like,
Yes.
yeah, could be.
Yeah, but
you know who believed in us?
who?
Mr. Gibson from McDonald's.
I was gonna say you can't say that without going back and telling the story of McDonald.
Well, that's all him. But I was just gonna say, like, he said that because I remember when he started to think of automation, and you should talk about Gaia, by the way.
Yeah.
But when we had this conversation, we kind of put this together. Talk to. Well, you should tell the story.
All right.
But we were crazy in the right way. Let's put it that way.
Yeah. It seemed like, well, the thing is, like we we're still not there yet, right? So like the humble origins are like we're still there.
Hey, that kind of brings it back to the very beginning of the episode, right? That's ambition. It's like, yeah, we're here, but we're not there yet.
Right. It's a journey, and there's so many parts involved with trying to get like this thing to actually function the way that we want to. And so like the idea was for automation. So we made a group for we made a group for the advancement of instrumentation and automation, and that's called Gaia, right? So that's it's exactly what the group was meant to do. And in this, like I worked on several projects to try to, it's essentially just the upkeep of the things that we have now, but also pushing those things to new limits, right? So one of the things that we like, for example, something that we're lacking as an observatory right now, even now, right? So one of the things that we're lacking is like a spectrometer, right? We don't have a spectrometer. We don't have a spectrograph that we could use or install onto our machine. So one of the projects was to actually create one. So we have the humble beginnings of one sitting on a table on an optics bench at the university. And all it is right now is one of the gas lamps from the physics lab. Actually, no, this one was ours from the demo equipment that we would use for public outreach. We have a gas lamp that you have there's these diffraction gratings. But I think also there was, a lot of people aren't aware that they've handled diffraction gratings before. There's these large events where people would go, where they were hosting, music of the electronic kind, and they would call these festivals. But every once in a while, you would see that there's these people that have these glasses, or they would be selling them or giving them, and when you see through them, like you would see these like cool shapes, but with rainbows. So like there'd be stars, but those stars would look like rainbows, and those were essentially diffraction gratings, except that they have the shape etched into it, so you would see whatever shape was etched into it, but as a rainbow. And and that's essentially the basic part of what a spectrograph, or the basics of how it works. And so we have that set up on the table, and we were able to look at that. And and this was something that was done entirely by students. So like who was there? There's Brina, Leanne, and Wendy. This is something that they did. Yeah.
So hey everybody.
Hi Brina,
hello.
Leanne, and Wendy.
Can I ask a technical question? Just real
Sure.
quick detail. The gas. Are you using a particular gas? Like, what's the purpose of having the gas tube?
Oh, right. So the gas tube. So when you apply some like electrical current through that gas tube, it will energize the gas molecules that are in there. And upon energizing it, the electrons that sit on the outer shell of that, or at least in the model, right, in the outer shell of that, they jump to a higher level, and then they go to a state of relaxation. It's a spontaneous process where during that you have to have some loss of energy in some form. And so when the electron goes back down to the smaller energy level, it shoots out a photon. And that photon is at a very specific frequency. So it's a very specific wavelength of light. And that completely depends on on that energy hop that it did. And that energy hop is very specific to whatever element that is in there. And so this is essentially how we can fingerprint the elements in stars. So that's why it's of interest to us, because if we can do you essentially need one gas tube to be able to calibrate, like the positions of each like the relative positions of each of the bands that gets generated, right? Because since it's a very specific wavelength of light, or it's a specific group of wavelengths of light, you can measure that relative distance from one to another. So then if you pop in any other gas tubes or combination of gases, you would be able to pick out what combination those are. And that's essentially what we want to include onto the telescope. That way we can do this kind of identification, this fingerprinting of elements in other stars.
And which gas in particular are you using as a calibrating source in this?
So I'm trying to remember. Actually, I don't remember.
I think it was either hydrogen or helium.
Yeah, I think it was helium. I think we were using helium. Yeah. And why that one? Because we had it. Yeah, that's pretty much it. We were doing that one because we had it. And I don't remember, I really don't. I really hope that we didn't have like an easier one to use. Like I don't know if you guys heard the story of the person who like made the first ruby red laser. That at least the story, the way I've heard it, was that and this is something like back in like 1970, right? So like right in the beginning of that, there was a paper written much earlier than that that said 64. That right, 64, that lasers should work, at least in principle, in theory, but
I should correct. I'm sorry. I thought you were going to say something else. No, that's way earlier than 64.
Oh, okay. No, well, what are you thinking of
the first development of a ruby laser in experimental testing, like an actual
yeah one. Yeah, exactly. Yes. So not just the paper showing that, but an actual ruby red laser. Okay. They apparently, the way that they chose to do it, like the particular mode, was probably the most difficult to actually produce. So because it was so the tuning of everything had to be so precise for it to work. And the incredible part was that they're actually successful in doing it. And so like this was phenomenal for everyone in modern day. Yeah.
I mean, you can generate lasers a lot of ways, but speaking of helium, you might have heard of Heine lasers. So like that's a mixture of helium and neon gas, and you excite them, and that's one of the sources of the laser emission. I actually thought of a scientific application for using helium as a source. Hopefully it is helium, because then you can then test it on the sun, the spectrograph on the sun, perhaps, like even coronal, like you can get a coronal imaging with the telescope and see if it's close, like as an astrophysical calibration source.
So that's cool.
You could try that, but Moises and I have tried to image the sun before, and don't point your telescope. Yeah, you need the right equipment. I mean, we didn't do anything necessarily destructive, but it's difficult to look at the sun with a telescope.
Yeah, we just so everyone is aware, right? So like what we did was we had a filter for our telescope.
Yes, but do not point your telescope at the sun, period. That's just like that. Just let's start at that level right there.
Yeah, they also have stickers on the telescope that say "Do not point directly at the sun."
Even through like with the Dobsonian I have, like you point it at the moon, and the amount of sunlight that it reflects, that hurts your eyes. You stare at that for a few seconds, and your eyes will hurt. Like I can't even imagine what instant blindness looking at the sun.
It would be.
Yeah.
It would also destroy the telescope. Because you imagine the telescope's like building coherent light, so that would just self-reinforce and it would just warp and destroy the mirror. I don't want to imagine that. But frankly, that's so.
Yeah, it's like if that the magnifying glass, there's some people that like to test it on themselves, right? If it can burn paper, right, it can most likely burn your equipment.
The closest I felt to that was like by bumping an infrared laser. There was an infrared laser, something like I think 800 nanometers or something. So you couldn't see it.
Slightly out of the range that we can see.
And like we were supposed to pass it through a crystal that dropped the frequency by half. So what would happen is it would go in invisible and it would come out blue, and you could see it.
That's
and
so cool.
But like if you put piece of paper or something in the invisible beam, suddenly it would just like almost just like light on fire, and there would be a hole. There would be like a hole in the paper. So
yeah, that's a powerful laser you were there.
yeah, it was a 5-watt emission from the primary source, but it could go up to 10 watts. That was with I believe, okay, this has been years, but Dr. Lytle and Dr. Gagnon from Franklin and Marshall College, their optics lab, which was my first experimental physics research experience.
That's so cool.
Learned a lot about lasers with them, and yeah. Anyway,
fun fact that blew my mind when I first really learned about lasers. No, it wasn't until a couple of years ago that I learned that laser, because I mean, we were talking about acronyms before too, and laser itself is an acronym, and I thought that was the coolest thing. Wait, what is it? Let me see if I get it right or wrong. But light amplification by stimulated emission of radiation. That's correct. Laser.
That's it.
So,
and the predecessor of the laser is the maser. You've heard of the maser, right?
No.
It's microwave amplification by stimulated emission. Yeah.
Okay.
Fun facts.
I think laser is just like the coolest sounding word that came from also a pretty cool acronym. I just kind of set the stage.
It was a really, it is a highly technical word that came from within physics, and it's one of the few that I think impacted general just vernacular, right? Like people say laser all the time, but it is actually a very technical physical event that occurs. It's not very well understood. You need to know stuff about quantum mechanics to really understand it, but it's used in everyday language, like the laser, and everybody knows what it means, pew pew, right?
What I picture is the cat with the laser on the wall, and the cat
oh yeah,
oh no. the unobtainable prey.
Yeah, when you think of laser boys, what do you think of first? What's your first thought?
Laser. I'm sorry, that's what
we're going to build a laser
on the moon. Okay. I watched a lot of TV. All right, so
that's good. That is good cinematography.
Yeah. My goodness.
So you mentioned Gaia. Maybe this would be the first public discussion of our Greek nomenclature. What else do we have that's Greek at CTMO right now?
So other things that are Greek at CTMO, specifically at CTMO.
Associated with. Okay. Okay.
So we do have. Let's see. Let me think. So
Zeus.
We have our Zeus is a project, right? So Zeus is a project that is one that Richard was working on. So I don't know how it is. It's been a while.
Still we could talk about that later after your stuff, but I do have updates on that.
Oh, nice. I'm excited to hear about this.
I've been working off the grid on that one. So
okay. Yeah. So there's Zeus. We have our machines. So in the observatory, we have a computer that's essentially the thing that holds everything up, and so that holds all the equipment. Yes. So we have Atlas, and Atlas is essentially the thing that's essentially the workhorse of the of everything there at the dome. There is also we have our machine that's dedicated. The idea is to have this as our dedicated processing unit, which is Epimetheus, and so it's a beast. that one is awesome.
Yeah. It's delicious, to be honest. It's just too good.
Yeah,
and I mean, ladies and gentlemen, it has 64 gigs of RAM and an RTX 2080 Ti GPU with linear algebra acceleration.
Yeah, and it's great for processing images.
Yes,
for this
absolutely.
Reason. Yeah, I did my thesis on it's essentially it leaned on being able to do a lot of image processing, because I was doing light curve, analysis. Actually, it was the entire process to get to be able to do light curve analysis. So I took the data, right? So, and the data I was collecting was on specifically eclipsing binary stars of the and this is the way I pronounce it and in my head. And so I know when I also gave my my talk for my thesis defense, I I also said this too, but I call them the W UMA type. And the W UMA type are the W Ursa major type. So we're talking about close contact binary stars. So like they have they might be close enough even that they're sharing material, and they're spinning around each other. So you can see, at least through light curves, you can see like if both of them are shining their light at you, or if only one of them. So like you'll get less light intensity when one is being blocked, and you'll get more light when both are visible. And you can track this pattern, right? This dance or ballet of giants. Mm.
Could you define a light curve just for those who might not know what that is? Like, what
Oh,
is a light curve?
yeah. So in this process of collecting data, so usually we'll look at some object in the sky, right? And we'll take an image, right? Our data that we do at the observatory is specifically like image data, because we do observational astronomy. And when we take the picture, it's at one particular time. When we take another picture of the same place, it's at another time, and another time, and another time. In my case, that time was, about 7 hours. So 30-second images for 7 hours. That was essentially my workday. Yeah. So, um, so I look at one star and see how much light was coming from that. And so then I can get some light intensity for that one time. Then I look at the light intensity of that same object at another time, and I do that, and I repeat that process. So then I end up seeing how the light intensity changes over time. And so that itself is the light curve.
That's beautiful. Yeah, thank you. And so you're looking at in your research and what you used on Epimetheus, light curves of eclipsing binaries, specifically UMA types, W UMA types.
Yeah, W UMA types. Yeah. And there's a reason for that. You know how I said that they're like so close together, they're like some of them even share material? Well, with that, something that also happens is that they rotate faster. So their periods are much shorter, which means that in one night I could actually complete one of their periods. So I don't have to, I wouldn't have to go, night after night to be able to complete one period, because if you study eclipsing binary stars, you'll see that there's actually some periods that extend beyond days, right? Beyond years. I think I most it is said that probably half of the stars that we see up in the night sky with our own eyes have a companion. And the companion may or may not be gravitationally locked, right, with the other one. So like there are some that are binary stars, but one is like in the foreground and the other one's in the background, right? So like they're not actually like going around each other. It's just it looks that way.
It's a visual binary.
It's a visual binary, exactly.
Yeah.
And there are others that are actually, in doing this gravitational dance around each other. And so that my main motivation was because of that, just because the period is so short. There is a star that is said to be a binary star, but like an eclipsing binary star, but we're talking about like on the order of like 200 years for a period. So that means like that light curve, if I take a picture today and I take a picture tomorrow, it's going to seem like it didn't change at all. So yeah, even like, I mean, I'm curious if there's anyone, well, I mean, ultimately everyone in astronomy, right, who is probably would be able to do this, but I don't think there's a dedicated project for this where it crosses multiple generations of taking data for one particular star to see if it's a,
Right.
you
I mean,
know,
I think maybe like Vera Rubin or like one of those large scale surveys will, I mean, because
will,
what, that's just those statistically improbable events. It becomes a question of statistics at that point. Just catch a
right.
large enough area of the sky.
Yeah.
Yeah.
Yeah. That's exactly it. I mean, we just need more eyes in the sky to be able to see these things. And usually observatories have projects, right? That the people have projects that they want to use an observatory for, which means that people have to sign up for that time, which means that the observatory um, gets used up differently. So it's never just like, let's look at this one thing, across, all of humankind's existence. And I don't know actually if there's any like multi-generational project like that. That'd be, at least in astronomy, that'd be interesting to know.
Yeah, maybe aside from like your surveys,
Yeah.
but I'm imagining like when, because I was doing observations with Arecibo as well at one point, and you would look at the observer schedule, and your slot was like 3:30 to 5:30 a.m. for this pulsar survey, and oh, there's 4 hours of maintenance, and then this grant is being applied here, and this person is working here, and it's just full. I mean,
Hmm.
the big observatories are prime real estate. It's very
Right.
hard to get that stuff.
Yeah. So if anyone's in school now, and wanting to become a professional astronomer, one of the things that you need to practice, something that I haven't actually done myself, is a proposal writing for telescope time. That like professional astronomers need to like it's part of
Right,
their
and
bread and butter. Yeah.
sorry, I'm getting excited.
Yeah.
I don't mean
I thought
that.
you were going to say sharing. One of the things you need to practice as an astronomer is sharing.
Actually, well, that's true. I mean, you'll get like for some of the big ones, you'll get a few hours of observing time in the year. You might get like 2 nights at McDonald if you get like something on the auto Struve, a couple of nights maybe. But then there's also, and this is something I wanted to also talk about too, is the time domain stuff, because like every
Mhm.
observatory has a project. So CTMO is teaching people, and it's primarily functioning in time domain, training in time domain. Um, you might have astronomers who are looking at objects that or events that occur that could be really worth your time to spend time on, and so they might get dedicated target of opportunity time. So like if a gamma ray burst happens, I could trigger some of that time. I get 45 minutes on that scope, and then just like it's almost like I have an amount that I could spend over the whole year or over the whole grant term, basically.
Mhm.
um, so but yeah, definitely getting to know that process is important.
Yeah. Yeah. And it seems like we might be heading towards that direction, right? So, but at the moment, it still seems pretty open. So the students get to pick their own times, and but as Victor said, we do share. It has happened where we say like, hey, because the goal is for the observatory to be functioning every possible moment that it could be functioning. Like that's the goal for the observatory. And like let's say I'm no longer in the regular observer schedule as I used to be, but like for example, like maybe Victor's doing an observation, right? So then like I can be like, hey Victor, can you get me I want to see this, and he'll be like, let me check my busy schedule here of this science I want to perform, and he'll be like, all right, sure, I can squeeze you in.
Yeah.
Yeah, yeah.
I, I think like wouldn't it be a pretty cool like a citizen science thing? I didn't know that it was such a competitive market for to write proposals for that. Wouldn't it be so cool to do that like in Brownsville, like have
Yeah.
high school kids or something write their own proposals about why they should get time at CTMO and then let them go do it.
CTMO and SLO too. You could have
Yeah.
two. I mean, um, the one that I draw inspiration from, for, at least for remote access, is the Burke-Gaffney Observatory in Nova Scotia, which I've triggered a few times. And it's like a Twitter, or I think you could send it now, a Facebook message, a text, and I send it by email, but you could send like a Twitter and like the hashtag acts as a command. So it'll be like hashtag exposure time, or like hashtag this object, and it'll put you into a queue, and then it'll say, oh, here's a link to your image, and you could download the FITS image of that in different filters. It might not be immediate, but it's pretty cool that you could trigger these things from the distance and have it seamless data transaction.
Wow.
Yeah, I'm sure that's very similar. I mean, I've seen you're using, what's the program that you're using for remote access in the telescope, the mini domes for the high school students?
So for the mini domes, we're using one that's it's open source. It's called K-Stars. K-Stars is the name of that one. Yeah, and it's really nice. Like in terms of its functionality, like the ease of use, I think is pretty accessible for people. And this is what we use in the astronomy labs themselves. So it lends itself nicely because like this project is a community driven project. By a community, I mean like the greater astronomy or amateur astronomer community, and
right.
They use a library that's called Indie, and it has a particular, like, that's an acronym too. I don't remember exactly what it's something about like independent something devices, and so they're trying to fill in the blanks. So exactly what they said.
Yeah.
But
it's actually funny because so far it does seem like every time they bark, they are like filling in gaps that we're not filling in. It's kind of interesting.
The D stands for dog.
The D stands for dog, exactly. But yeah, so with Indie, it's really nice because like using a Raspberry Pi, then I'm able to download drivers and install them into my into the Pi, and the device, I just plug it into like the telescope and the dome itself, the mini dome. I plug it into the Raspberry Pi, and now I have control over the entire set itself, right? The dome and the telescope through the Raspberry Pi. The Raspberry Pi is essentially like a cheap $35 computer that has Wi-Fi and internet capabilities. So I'm able to communicate either directly to the device, or I can plug it in and communicate over the internet to this thing. And so, and that's the goal for us. And with K-Stars, what's nice about it is that you don't need to know how to use, like, you don't need a virtual desktop to use those devices. If the drivers are running and the devices are plugged into the Raspberry Pi, I just tell K-Stars the IP address and the port number. Inside of K-Stars, they have this thing called Ecos, and it's like Ecos, like ecosystem, right? But they use a K, so they say Ecos. And they're inside of Ecos, it handles all that protocol for communications with these devices. So I download K-Stars on my computer, I open up Ecos, and then from there, I just tell it the IP address, the port number, and I say connect, and it just happens. It works straight off of my computer. There's nothing else that's needed.
That's amazing. And is this parallel, or I mean, is this distinct from ASCOM standard? Like, is this a different platform, and it's using, or that and POTH, of course, because I can't go without saying POTH. I mean, come on.
So this is these POTH jokes will make it impossible for us to go into the future.
There's a remember the sign POTH coming southbound on I-69 coming back into the valley.
Oh, that's right. So if you've ever done that drive from San Antonio down to the valley, you'll just leaving San Antonio, there's a sign there that says POTH. And we went through multiple times, driving like for different conferences and stuff, and we always saw that sign, like,
POTH.
Yeah. But POTH stands for Plain Old Telescope Handset. And so the idea with POTH was that it's a virtualized controller for your telescope. This will date us, so people will actually know, like, oh, this guy's an old timer, because they got rid of
boy.
POTH.
Oh yeah, they did, because
Yeah.
that's no longer up to standard or anything.
No. So ASCOM is the astronomy standard for like using COM ports. It's not exact, like I don't remember the exact name, same way like with Indy, right?
Yeah.
But it's, if I remember correctly, it's something like that. It's just, the astronomy standard for COM. And COM is the communication protocol that's used on Windows machines. So I I I dug in deep, and so this is one of the things I've been working on most recently, which is using ASCOM. I dug in pretty deep, and yeah, so I learned a lot about ASCOM and how it works. And so with ASCOM, it's really neat. At least the concept of it's really neat, because now um, there's a thing called Device Hub. So ASCOM Device Hub, it allows you to plug in your devices to communicate to Device Hub, and then Device Hub can then send the signals of all your devices to multiple programs at the same time. And but it's Windows only. That's the only thing. The people at ASCOM have like, it is there's a small team. I think it's 3 people. They've worked on this new standard, which is called Alpaca. Like, so there's ASCOM Alpaca, and with ASCOM Alpaca, it uses the same type of communications that you would do over the internet. So this net communication, you're able to communicate with devices just based off of like IP and port numbers. Yeah, and so you can send commands directly to the device. But ASCOM didn't exist. I don't think it existed before 2000. So in terms of time, and in terms of like things like standards that exist, it's not that old. And so
That makes a lot of sense too, just for historical standpoint, because like the early 2000s when your go-to mounts and your CCD cameras started to reduce in price and come onto the regular consumer market. So I think that standard that's not random that it was adopted at that time, around that time, I think.
Yeah, and luckily the guy who like thought this up was like, this is a problem, because right now the only way that we would be able to like function to do astronomy would be as at the consumer level, right? So not for research. So just like people, or everyday people, the way that they would have to do it is like, they would be dependent on a company to make the device and to make the software that controls the device. And like, for example, we use like Maxim DL, which is a popular like observatory control and like image acquisition software or package. That actually doesn't, like, you're not restricted on which cameras you can use, because they have different drivers that will communicate to Maxim directly, right? And so usually we don't think about these kinds of things, right? Like, I plug in my microphone and it works. Oh, that's it, I'm done. But here, like, if you have different people making this stuff, particular astronomy, which is a bit of a more of a niche market, right? If there aren't that many people getting this stuff, then maybe there won't be that much need for these kinds of stuff. But since this guy started, he's like, this is an issue. He's a programmer too. He's like, let's make these standards now. And so like they use this protocol, and like there was a lot of back and forth between the community and manufacturers and amateur astronomers, casual astronomers, just trying to do this at their own homes, right? There's a lot of back and forth on how to do it, and it got finally, like, after 10 years, like, it got set. ASCOM got set as the standard for all of this. And so I think I should say, like, it got after that time, similar thing happened with alpaca, right? So like there's other people, like for example myself, I'm running these programs right now off of a Mac computer, right? And there are other people that are like Linux users, and ASCOM is specifically for Windows. And so people are saying, when are you going to Linux? When are you going to Mac? And this is where Alpaca came. So before, the market was very heavy, like Windows, but more recently, there's been more of a transition where more people are having either Macs or exploring Linux, and then there's people like us that are in between the worlds of research and and amateur astronomy, right? Where we do this because it's like we want to study it, but we also like to look at pretty things.
Try to strike a nice balance between the two usually.
Yeah. And yeah, I'm like, it'd be cool if I can use my Mac to control it rather than having to use another computer to do this. And yeah, so I learned a lot about ASCOM more recently, and that's one of my latest projects that I'm currently working on right now.
So ASCOM is closed source, right? It's not open source,
So ASCOM is a standard. So
oh, it's not a code, like a set of code. Okay.
No, and
see, this is more into your area than me at this point.
Yeah, so it's how can we call it? It's a shared library. It's a shared library of things, right? So in this library, they have sets of classes, and so for different types of devices. So like you have things like if you want to communicate with a camera, they have a camera class. And so if I want to communicate using ASCOM protocols, they already have all those functions written for the camera. So as a developer, one would have to just make sure that like a manufacturer would have to make sure that their device has like they match up with the existing functions in that library.
Mm-hmm.
So, and that's essentially like the biggest hurdle, right? That if you, because you could make your own device, right? So like you can make your own dome controller, you can make your own go-to mount controller, and but the thing is, you would have to figure out you have to establish your own protocol of how your device wants to receive communication, and you tie it into the ASCOM communication.
I see. Yeah, so there's like a market pressure essentially to adopt that, because if you want it to be sold on the general market, people are mainly using ASCOM standard. So
right. So actually, I think it makes you more marketable, right? So like if you write a program that like check this out, I have this astronomy software that you can use. It looks really nice. It's really simple to use, so you can get these awesome images of like distant galaxies. Or we call them deep sky objects, right? It would be nice, right, if you just plug it in and things worked as a user, right? And without having to do like a lot of fancy stuff. And ASCOM allows people to do that, right?
Mm-hmm.
So for something, let's say for a device to say it speaks ASCOM, and for a program to say it speaks ASCOM, that means it could be whatever device, right? And whatever program. It doesn't have you're not just locked into using, a specific program for a specific device. You can use any device for any program.
Kind of like Bluetooth connection even, or anything that has a standard connection protocol.
Oh, yeah, exactly, right? So like, it doesn't matter what phone I'm using. If I'm using Bluetooth, I can connect to whichever speaker that also has Bluetooth. That's a really good example. Yeah.
Okay. It's interesting. Yeah, I'm trying to flesh this out for a lot of people who might either be interested in getting into amateur astronomy, and the number one question that at least I'm always asked is, well, what telescope should I be my first telescope? But if you're interested in astrophotography, then you're going to need to get used to this at a basic level because of the imaging and also the tracking of the mount itself.
Mm-hmm, mm-hmm.
So
yeah. And we're back.
I have a question for you. It's kind of out there though.
Okay.
Can stars change colors?
Can stars change colors?
Like a
Can
single
stars?
star could, like a one star which is like one color, change its color ever?
Yes. That's essentially that is that is the way essentially that we age stars. Like that's how we tell the age of a star by that. So that means like the in order to figure out its age or like its type, um we are able to label it based off of the color. I mean, color itself, it depends on the wavelength of light that we're seeing. And when you look at the like the entire spectrum of that star, it's not just a straight line. Like it's not just like full blast boom. Like it's all these it's a combination of different wavelengths of light. It's not just like one specific wavelength.
Mhm.
And so what's interesting to see about that though is that it's the curve follows a particular path. And for those who study physics, you most likely heard of black body radiation, and the light curve. I mean, like the specifically how the spectrum is in terms of intensity of that star will follow that same kind of path that the black body does. And so and it's an interesting concept because like internally you have this energy, right, that's trapped inside the star, and it leaks this energy in the form of light where we can see it. And depending where that peak of intensity lies, its wavelength, we can determine then what the temperature is. Based off of that, then we usually what we'll do is we'll put them into what we'll classify it, right? We use what's called the spectral classification, and from that we're able to see where, with relation to other stars, that star is. And we have this general idea of how stars evolve, and it just so happens that it follows this trend that completely depends on the color.
Yeah, and that's interesting too because like you can astronomers can then define things such as metallicity from the color change as well. I mean, that's how you age. You mentioned age of star. It's how you age galaxies and the evolution of gas. So anything, basically all evolution that we understand, at least outside of cosmological, theoretical stuff, is aging things based on color change. Ultimately, at least
Mm.
from an observational standpoint in the optical wavelengths. And astronomers define a physical parameter. It's a ratio of amounts of stuff, and that's called your metallicity. So the amount of iron specifically to hydrogen is this metallicity ratio, and that number and how it changes with time is how you age things and how you can tell how galaxies and stars and different things like that change with time and evolve. So I'm glad you said that about age. That's really important.
Yeah, so naturally the next question that people would be curious about is where does our star fall in relation to other stars and age and color and well,
Yeah, the what's interesting too is that in general, depending where it lies in this is also the size. So that like there's just a funny relation between the spectral class and the size of these stars. And so so if you're in the astronomy labs, you'll know that the sun is a G2 type star, right? So I think it's so funny, like the just history of astronomy. We keep all the old stuff. It's one of the oldest sciences, right? Um, uh, One of the oldest sciences that exist, like and documented sciences, right? So like we're talking about like way before BC, right? So like BC, and so um there's ancient texts that have these relations about stuff, and
Even the
so
dinosaurs had astronomy.
it's I mean well I mean they looked up at one point. Oh man, that's a mean joke.
They looked up. They looked up at one point and the last point.
And the last point, yeah. And but like there are things that like get set back in the back in the days, and they just keep going even in modern days. And what I think is really funny, and it speaks truth across all the disciplines of science, is that because somebody said this one thing a long time ago, they keep the way that they said it back then, even though it might not completely make sense today. And so like this old notation or nomenclature, or like in this case the spectral types, they use a letter format that isn't in alphabetical order. So if you want to know what order it should be, then I myself look up a chart. So I don't know
Yeah.
off the top of my head. I know it's like O, B,
AFG,
AFG,
KM.
yeah. And so and this is another thing for the students that are in the intro to astronomy. I don't make them memorize it just because I could look it up in a chart, right? So that's not, I don't find myself, I mean, I could be schooled at some point and told another reason otherwise for them to have to learn that particular, that particular order means these things. But I mean, if they can read it off the chart and understand what it means, then that is better success in terms of the learning process, in my view. But yeah, we're G2, and if you label the G2 star, we sit right in the middle of the oh man, the word is slipping my mind.
The life cycle.
Main sequence, yeah, no, main sequence, yeah. So like
that's the main sequence on the Hertzsprung-Russell diagram.
Oh, that's right. The main sequence. So we are a main sequence star where most stars live most of their lives, and like we're still like in the early to middle stages of the life of our star. So like in the evolution process, our star will start becoming larger, right, and become redder, right? So going back to the thing of your question of do
redder.
Oh my, it's not shy. It's not shy. Yeah, so in that process, it'll start becoming a red giant, right? So
we'll be inside it, right? I think yeah, or at least we'll be very close to the photosphere, which is the surface of the sun, right? So
yeah.
Again, I'm talking to a big audience. The one thing I wanted to add was about variable stars. I saw an interesting fact the other day. I didn't realize it, that the sun is technically considered a variable star. It varies in brightness by 0.1% over its 10-year solar cycle, which is interesting. So like even the sun, which is considered a well-behaved star, which we don't really know historically speaking, we just know for somewhat of its lifetime, it could very well change in variability more, but it is a variable star. So like, as you were saying to your point earlier about most stars being eclipsing binaries or binary systems or variable stars in general, the sun does have variation over time. So I thought that was pretty interesting. I know some stars though, they get bigger and smaller, like noticeably, right?
Oh yeah. So they pulsate, and through that pulsation process, their light intensity is like bright and then dims and bright and dim. Yeah.
Parties on that planet must be awesome. Like this.
All right.
What's the one? Has anybody ever read the One Hitchhiker's Guide, where there's the loudest band in existence, where when they play a concert, they're on the surface of the planet, but everybody has to be in space to listen to it. You can't be on the planet at the same time when they play, because it'll kill everything on the surface.
Oh my goodness!
Shout out to Douglas Adams. Yeah, sorry. That's yeah. So stars can change colors for a variety of reasons.
Mm-hmm. Yeah, and that's essentially where we're at in terms of our our star, right? Our sun.
Yeah.
What was the most interesting thing you learned about stars that made you fascinated by them?
The most
Or was there
interesting.
a specific, I guess, sorry, let me add a little bit more to that question. Like you started off talking about your curiosity and how you just wanted to learn how things worked. Was there anything from that led, so that's what led you go into physics? And then from that, was there anything else that about stars specifically that led you to doing your research based around variable stars?
That so the funny thing here is that it was more of a like historically because of a practical thing. So like because the opportunity to do that specifically became present, that is what I did. So it's not that I had like envisioned that I would have studied something else in astronomy. Like I myself actually didn't think I would be studying astronomy. So that is like one of the truths of me and where I'm at now, which I find very surprising. You know, like what year are we in? We're 2021. So ask me in 2011, so 10 years ago, if I would be doing astronomy. I didn't think I would be doing astronomy the way that I'm doing astronomy today. Like that is true. uh yeah, I was thinking, and at the time I was working on that project that was more like is a mix between material science and essentially just like engineering and design. um I I was looking specifically at trying to see um how the substrate of the welding that they do for the test mass mirrors that they use in LIGO. So they have like these huge like glass mirrors, and they use those to shoot a laser right from one end of the lab down this 4 kilometer vacuum tube that hits this mirror. That's probably, I don't know. Actually, it's kind of big. It weighs a lot. It's if I remember correctly, what was it, like 80 kilograms?
It's
Right.
20, but at full it'll be 40. They're going to upgrade to 40-kilogram test masses.
Oh, okay. So
I
I
think
don't.
so. I think.
I don't remember. That's one thing to be said. I don't remember. And also I'm not that very close to the project, just a little bit.
Don't add
And
us, LIGO.
oh no, I'm sorry. um, I'll make sure I learn more, and and I'll share that with the public, right? In terms of the technical aspects, but in like in its simplest form, right? They shoot this laser down and it's actually two tubes. There we go. Two tubes at 4 kilometers each, and then there's a glass that they reflect the light from, and the way that they try to eliminate any potential noise or vibration that could be coming through that glass is that they actually hang it off of another identical piece right above it. And above that one they have another platform that will actually shift to compensate for any movement of the ground, any mechanical movement. And meanwhile, the second mirror will act as they have it's an electrostatic drive that will nudge it ever so slightly to remove any resonance uh, traveling forward on that bottom piece. Now, those two pieces of glass that are hanging one above another are mechanically or like physically attached, and the way that they're attached is through like all of this is all silica, like it's all fused silica. And so it's literally just welded glass with these two threads at their thickest point. I believe they're or at their thinnest point, I believe there's something like 2 millimeters. And so there's two millimeter threads on both sides that are holding on to this like really heavy object. And my original project was to see how right, because when we have this thing that's stuck to the side that's holding on to the threads, to see how that shifts in time, if it does shift, right? There's a lot of, since it's carrying so much mass, it's thought that it should shift somewhat, and we're curious to see how how that shift happens across time. But yeah, that was a completely different project, right? Like, it contributes to astronomy, but not in a direct way, you know.
Yeah, that's like even more like engineering, specifically for those interested in that. That's like feedback systems and actuators, and which is very difficult stuff to do.
Mhm.
I remember seeing a lecture before on how like that feedback system, just like the basics of a feedback system, and it's um, apparently with like a lot of mechanical systems, it could be quite catastrophic if you don't get that right, because you're trying to suppress resonance, right? Like when a buildup of something. I'm thinking of like the right tempo of walking across a bridge could destabilize it. So having something that removes resonance or essentially dampens resonance could work if it works wrong very catastrophically. So yeah, and there's like multiple test masses hanging off of each other, and the top one might vibrate by the time it gets to the bottom. That dampening effect takes hold. So it's really fascinating how simple but effective that principle is.
Yeah. And so that's probably the main thing, just from a practical standpoint, that like that my project, like my advisor, right, said like, I need help on this project. So immediately my project shifted from more on the engineering side to observational astronomy, and then from there, the variable stars I thought was pretty cool, because like over the course of a night I can see that change happening, and from that information I can pick out some information, like how big these stars actually are, like the actual physical diameter of these stars. You could also see you can guess their masses just depending on the rate at which they're actually going around each other. And with our current technology that we have at the observatory, it's very limited the things that we can do. And that's essentially the biggest push, and the reason why we need that spectrometer, because you need to see how the colors change, because they actually, just the fact that they're moving away from you will change the color of the star. So that's another way. It's not that the star itself is changing colors, but the fact that they're moving away, you'll see that shift in color.
You'll also see if you're looking at objects that are cosmological distances like quasars. So you can get the quasar emits light, and so, depending on its angle, it could be absorbing some of that light. So you see absorption features in that spectrum, and you could tell like, oh, that cloud is made of this. But since it's at cosmological distances and it's moving away from us, there's two terms. There's a redshift term from its proper motion, and then space-time, which is expanding, also induces a redshift effect. So when you're looking at really far away objects, they're moving away from us for two reasons. They could be, right? The proper motion could be moving away, and space is also, right? So,
Yeah. What is space?
I'm so glad you said that, because I was literally going to ask you that. I was going to say, Moises, because I know you told me this before, I believe, was space. Like, what is space has been a very curious question to you, right? Like,
yeah,
people ask what is time, but you're like, no, what is space? So
this is
go ahead. Just
no, this is just something that bothers me so much. Like okay, I talk about my like being curious about stuff, but this is a bother. Like, I don't know, like it's like a weird feeling. Like, people think about time, and then like they're like, what is time? Like, are we even here now? Or are we just echoes of what happened before, and like now our consciousness is catching up to that thing that happened? Okay, this is completely like,
never heard that, but okay.
Ladies and gentlemen, buckle up.
Okay, I'll entertain those ideas, but my question is, what is space? Like, I don't understand. Like, I don't even know how to start even like chipping away at it, like,
right?
like there's I don't know enough to be able to have these concepts, and like I don't know, like I don't know.
Right. I mean, even with remember the last time, Victor, we were talking about how when like a gravitational wave occurs, that's like, okay, so like space, we know that there's geometry attributed to space, whatever that means. Like,
Yeah.
and that geometry can change. So like a gravitational wave is some periodic change of the geometry. But then if you want to measure that and you put a ruler there, the ruler will also change in size. So like
Yeah.
even to measure, like distance is not a trivial concept, because what are we talking about by distance? Are we talking about coordinate points, or are we talking about actual physical separation? Right? Because like with the gravitational wave, that could cause me to get closer to you temporarily in one sense. Like Moises could watch it happen. But if I were to put a ruler between you and me when that gravitational wave passes, the distance between us has not changed because the ruler has gotten smaller. The coordinate system is still the same coordinate system. So that's why space is very interesting, because how do you even measure it? What are you even talking about, right?
Yeah, like I don't know. You know, like I was very fortunate that I was able to take a class, right, in general relativity, and it highlighted there the like I didn't know what the meaningful impact was of like the fundamental equation that is like the Einstein, you know, wrote when talking about general relativity. Like I was like, okay, there's an equation that exists. He did some stuff, and so what? And but really, I mean, yeah, like I don't know what is the meaningfulness of it. Like, sure, okay, um we were able to see that like light can actually bend because of masses. Like, okay, yeah, like that's weird, but why is it meaningful? And this is like like the importance of understanding just the theory. And you know, just putting it out there too, like when we're talking about theory, we're talking about this framework, right, of this construct that we apply rules to. It's not so much that it's like, oh, I have an idea, right? But instead it's these rules that we build up, and we use those rules to then be able to generate other ideas. And
Right.
in this case, the idea from the Einstein equation for like the fundamental GR equation, I finally saw it and I understood it, which was like, at least in its in a topical sense, right, like in what it means, right, in terms of understanding is a completely like in true understanding in the depth of what it means is something else, right? But what it's showing is another thing, right? So what it was showing was that on one side of the equation, it talks about only things that are geometric, nothing else. It's only things that are geometric. And then the other part um, are things that we actually measure and see, right? And particularly talking about mass. And so mass and energy. And so this is so weird because one thing is only talking about shapes, completely like abstract idea. And then the other thing is talking about things that we can actually measure.
Right. So,
And
like, ladies and gentlemen, just to reiterate, it's that energy. His insight was that, in a very topical way, as Moises said, energy affects geometry, literally. Like, you have a triangle in space, and you put like energy near it, or which is mass, right? That triangle is going to change. That's very strange. That's a very strange idea. So, I'm just reiterating that, emphasizing that.
yeah, and so, and I'm like, to me conceptually it's like, okay, so I have this thing, geometry, how can I apply it, you know, to the things that I see, you know, like essentially part of the rules that we use in physics and coming up with these, with theory just in general, is that we should always be able to get back to like the thing that we learn in high school physics, back to Newton's physics. And that's one of the things. Why? Because those are the observable effects. So these are things that we see, tried and true. If I drop a ball and I have a stopwatch, then I get a particular measurement. So if I build this framework that also includes this kind of motion, I should be able to apply those. I should be able to get back the original quantity that I would have received for the amount of time that it took from that other theory. So it's I wouldn't necessarily say backwards compatible, but there needs to be some kind of compatibility when applied in that way. When we're talking about general relativity, right? We talk about gravity. Gravity is one of the like the parameters that is used in that equation. You get back gravity, so you could essentially figure out how much you yourself, your mass is causing light to bend. But the thing is that like you're going to see 0.00000. The effect is going to be so tiny that essentially is what's the point of doing something so complicated to figure that out, right? Some people will argue that like because it's cool, or maybe I can find something else out. But the thing is, in terms of practical sense, what does that mean, right? What does that mean to you? And in terms of practical sense, driving, I'm driving, there's this geometry, I see a sign that says 30 miles per hour, I look at my speedometer and it says it's 30. I'm like, okay, I won't get pulled over for speeding. But that's in the practical sense, right? I want to make sure I have enough distance between me and the other car. But there are other things at play, right? So like I was in the car and I had a rock like had fallen in my shoe just before I got in the car. And so like I pulled the rock out and I had the rock in my hand, and I was driving right with this rock in my hand, and I'm thinking to myself, if I were to like, and I had the windows down, it was a beautiful day that day. And so like I had the windows down and I'm thinking, if I drop this rock would be traveling at 30 miles per hour. I don't want to hit anybody, so I'm not going to drop this rock at 30 miles per hour. But to me, it's like nothing, right? We right now are traveling around the sun, right? The sun is traveling in the arm of our, one of the arms of our spiral galaxy, the Milky Way. So the sun, like we're moving around the sun is also moving around, the center point of our galaxy. And I don't even know what the galaxy is doing. Like maybe is the galaxy also traveling somewhere through this thing that we call space? And this space is something that exists between all of us and everything that we're made up of as well, right? So like, this is the thing that bothers me so much because
Yeah, me too. I remember from our first the conversation we had before where we were talking about the Big Bang, and that was something that what bothered me. I was like, okay, so the universe is expanding. It had to expand from one point. Then you guys had to explain the concept of no, that point is everywhere. And there is no one point where everything is expanding out. It's like there's some things expanding this way and there's some things expanding the other way, but they all came from the Big Bang. And that's just something that was very difficult for me to wrap my head around too.
Yeah, the fact that there was like a beginning point and nothing before that, because the Big Bang didn't happen. That's the misconception, right? The Big Bang didn't happen in space. It was of space. It was an expansion of space, all space. So like everything was at a point. It's not like you could look at the point from the outside and regard it. It's that everything that exists is in that point.
Yeah, because I feel like that's how it's communicated, right? Like everything at one point was in a single point in the whole mass of the universe, and then it expanded, and then the Big Bang happened and it expanded. And so in my mind, and I'm sure in a lot of other people's minds, it was in one point and then it came out from there. And so I thought, oh, cool. So somewhere in the universe, there was a point where everything came from.
It's more like everything in the universe was at one point.
Yes.
Yeah.
It's not that they didn't come from a point. They were all,
Right. But it seems like and this was the misconception that the original thought that he had, right? That's what I'm understanding, right? That you thought that like, oh, we can just track everything back to where everything.
Yeah, I thought that if you were to just rewind it from the point of the Big Bang, that it would be like, here's that one point where everything in the universe derived from.
Yep. Yeah, and that's it's really hard to imagine. I mean, it's just as hard because like you could say in kind of a stated sense what the Big Bang is at one point there was no yesterday, and suddenly there was an expansion of that point. Like all things were that point. Your entire coordinate system was in that. It's not like the coordinate system was out there and suddenly, and then you could say, oh, it happened at the origin and now the galaxy is some distance away. It was that the entire coordinate system converges to that point.
Okay,
And
that
there
makes
was
a
no
lot of sense.
and there was no yesterday. And I usually draw the analogy, like, how do you imagine there was no yesterday? It's hard to conceptually, but like from a coordinate standpoint, I think I brought this up before. When you go to the top of the Earth coordinate system, there's a point where you get to the top, and no matter which way you go, you're going south. You can't go more north. And so from that perspective, you can look at time in a very similar coordinate sense, that you go back to some point and there's just no point before it. And it seems like that would be an inconsistency, like, oh, how does that make sense? But we take it for granted all the time. That happens in a lot of situations. So yeah, Sean, I know we need Sean Carroll here. Sean Carroll, you need to correct me with all of these things and explain to me what's up, because
yeah, so maybe this my question of space lies in cosmology or something. Like I need to think of other things, because like this whole concept of space is something that exists across all scales, right? So the space exists across all scales, except that there is this supposed limit of smallness.
the limit comes from like when you apply concepts of space given to you from GR at the quantum level. At one point you fail to make predictions. So it could be that the Planck scale, as you're talking about, isn't the final scale, but it's as far down as we can predict, if that makes sense. Like,
Oh, I see. Okay.
yeah, it's just as the Big Bang, we don't know what the Big Bang is. We just know that when you apply the theories there, they fail to make predictions. When you go to the center of a black hole, it's not that there's actually a singularity, it's that we fail to make predictions there. And that's like, that to me is exciting. I think for you, if you did cosmology, like pursuing dark energy or something, because dark energy seems to be some intrinsic property to space that we don't understand. And I think we thought it was the quantum fluctuations, but when you actually calculate how much energy that would be, it's a huge discrepancy from what we observe. We would be expanding a lot faster. So like the open questions, dark matter, dark energy, they seem to be related to the concept of space itself. At least that's my understanding of it.
Would that be the same concept as like going the other way, like with the universes? Like I know they call it the observable universe because it's like this is as much as we know. Maybe there's other universes, but we have no way of knowing anything besides the observable universe.
Yeah, it's kind of like that, but there's, you know, with that that's actually there's different levels to it, right? Because there's parts that haven't come into our observable zone that will. There's some that will never. Like they were just expanded too far away at the beginning of the Big Bang, and we'll just never causally be connected to them ever again. But the thing about space, the thing about dark energy being a concept of space, because you look at all the theories. Okay, let's go to Einstein's equation. When you solve it a certain way and apply it, I'm speaking very generally here, of course, right? When you solve Einstein's equation applied to the whole universe in a certain way, you get an equation that describes how the universe evolves in time, and that's what forms the basis of modern cosmology. There's a term in there that's associated with dark energy, but it's just assumed. but all the different models of dark energy will say like, oh, there's a particular value at every point in space that just happens to be really small, that causes a small acceleration. That's everybody's familiar with that. That's like temperature in a room. Every point in the room has a value, and it's called temperature. So every point in space has a value called lambda that varies, but that over the largest area contributes to this really, it's the most amount of stuff in the universe we know is this dark energy. It's like 70%, and we don't even know what it is. And it seems to be an intrinsic property of space itself. So what is that? I don't know. What is space? I don't know.
What is space? And so this is also completely out of of my field of study. This is just something.
I think it's all outside of all of ours.
This is a personal thing that bothers me. Every once in a while, I'll think about it. So like this will be things that like, I mean, like we are held together by stuff, and there exists this space between all the stuff that we have that is us. Somehow we can still function, even though there's this massive space.
Wow.
Relatively massive.
Yeah, relatively massive.
I'm glad you didn't drop the ball on that one. That one's on these gravity jokes,
Yeah. It's like just like mind-boggling things in terms of distances and space. Also is like how I was told once that all the planets side by side fit between Earth and the moon.
Yep.
And I'm like, no way. So what did I do? I went into Stellarium and I looked up the diameters of the planets, and I was like, this is not possible. Like, how do things work?
Have you ever seen like those models of like the sun, like it's a clear sphere and they're filled with little beads, and it's like each bead is the Earth, and there's like a million of them or more in there. It's like
yeah, this is, and the thing is, I didn't know this until I think it was 2019.
It's pretty crazy, some of the stuff you learned, right?
Yeah, and so like I didn't grow up doing astronomy, right? So that wasn't something I grew up with, and so like these things, like I'm still learning things of astronomy, and so like it's all very still exciting to me, like I don't know, it's just so weird.
Yeah.
It
makes you look at the world different.
It does.
It is like I mean, yeah, me too. I definitely didn't grow up with astronomy or like even an interest in space until very, very recently. And yeah, and then like last year I learned about Rayleigh scattering. I think I'm saying that right. And the colors of the sun, like why the color of the sun changes when it reaches the horizon. And I can never look at a sunset or a sunrise the same without thinking about that.
Yeah, definitely. Look
if
at the moon.
sharing... Oh, sorry, go ahead, Moises.
No, I was just gonna say the same thing, looking at the moon.
Yeah,
that's what I'm thinking. Like now you can't look at the moon without thinking of all the planets. I'm not going to be able to now.
Yeah, that would be crazy. I mean, it would be beautiful for about a second, and then it would be pretty devastating. But it would be neat to be the moon of a planet with rings. Like if you were the moon, one of the moons of Saturn, and you have ring rises and sets, that would be pretty cool.
Oh, that's awesome.
Yeah. One of the things that I learned recently I didn't know about was the first distinction between the gas giants and the ice giants. Like when I grew up, it was Jupiter, Saturn, Uranus, and Neptune were all like gas giants. And then I learned recently why they're considered not gas giants. And actually Victor gave me a book to read about Voyager. And when Voyager passed Uranus and Neptune, it measured for all of the planets, for instance, the mass and the magnetic field and the spin and all of that stuff. And it found that for Jupiter and Saturn, you know how there's like poles, right? So imagine a magnet north and south. That magnet is aligned with the spin of the planet. So the planet's spinning like just like a basketball, and the magnetic field is pointed up. For some reason on Uranus and Neptune, the magnetic field is completely off axis from the spin. So something going on inside Uranus and Neptune is different than Jupiter and Saturn. There's something that keeps the spins aligned in Jupiter and Saturn. And in Uranus and Neptune, they're like, not to mention Uranus is on its side, but even still, the magnetic field's like 30 degrees or 40 degrees off axis from the spin. I thought that was so fascinating. It blew my mind. I just learned that recently. So
What? I just learned this right now.
well, thank you, Victor, and thank you. I forget who wrote the book. Who wrote that voice?
Jim Bell.
Jim Bell.
He was he was in the Voyager mission.
Highly recommend that book. It blew my mind. And that was all from, I think Neptune was like less than a 10-hour flyby. So most of what we know still to this day about Neptune was from one flyby that took like, few hours.
From here to Dallas, maybe.
yeah, exactly. Like from here to Dallas, but it was 2 billion miles away.
Yeah. That's funny because I think that statement still holds true even for you right now where you're at.
Well, everything's
welcome to Texas.
80 miles an hour and flat and straight. You can get anywhere in 2 hours. Yeah. Yeah, it's the only place I've ever been where I drove 12 hours and I still was in Texas, like Brownsville to Fort Davis or to Lubbock.
Yeah.
How do you guys feel about where we're at? I mean, we did this. We literally jumped in and did 3 hours. Like this was a 3-hour edit. This is the longest episode I've ever done.
And we can probably keep going, except I need to leave pretty soon.
Yeah, I know. I was going to say you have to be there for 7, and you should get some rest.
Yeah.
So, should I? I'll just wrap it up here then. Does that sound good with y'all?
Yeah, I think wrapping it up with Texas.
wrapping it up with Texas. Moises, thank you for being here, and thank you for having a conversation with us.
Yeah, thank you for inviting me and making sure that it happened. Yeah,
this is a very important discussion, and I hope you enjoy it. Well, I hope you come back for recurring episodes.
Yes.
Yeah, we'll need to come back and really talk about astronomy and the history of all that.
Yes. Oh yeah, absolutely. Yeah, we got to
get Tycho and his nose and Galileo, and
we got to talk about the celestial sphere.
The celestial sphere. Yeah, this is like the survey, right, of everything, and
survey of everything.
Yeah, and but yeah, we can definitely crack open a topic and go in depth for sure.
Absolutely. Well, I'm looking forward to it. So with that, ladies and gentlemen of Texas and the surrounding galaxy, these are Receding Horizons.